Hey guys, today we're doing probability and combinatorics as a topic stream, which are actually two quite related things, so it kind of works. I'm going to, let's see, as always, the standard things of Discord. Yeah. Okay, let's see, I hope everything's set up. First I should change the thumbnail to like something that's not, yeah. Okay, so let's see. What is the target audience for the stream? Well, it sort of like spans from beginner to like I'd say intermediate. There's no really advanced stuff like last time. It's sort of like the introduction and stuff. Let's see, did Code Forces remove my stream? No, it's still good. Yeah, okay. So basically we're gonna do these problems. And I guess first I will say what I can about this, although I will admit this is not my strongest topic, so it's not gonna be perfect, but I will do what I can. Let's see. I'm not exactly sure what there is to teach about probability. Like, mostly it's just you have a certain chance of things happening, and I guess there's linearity of expectation, which is something. But I mean, mostly it's like, yeah, I'll say the levels right now. Okay, so the first two are 1300, and then like the last three are 2000, and then like somewhere in between we have some 1700s and some 1800s in this range, and there are 10 in total. So let's see. Yeah. So probability. Yeah, this will also cover expected values, kind of. Although, like, there's a really good tutorial on expected values by Ericto. I linked that in the post. Let me. Actually, I'll link that right now because you can. It's a good thing. As always, setting up the stream as it's going on. You know me. Okay, so the link to the mashup is in the description. I will also put it in a pinned comment when it's ready. And yeah, you can also find a lecture on expected value there. So right off the bat, probability is just like, so the basic like binary probability is you have some chance, you have some probability p of something happening. Like you have, for example, an X% chance. Or actually, no, just say you have a probability p of something happening. And then what that means is that like either something happens or it doesn't happen. And probabilities have to sum up to 1 because something has to happen. Like it has to be one of the options. Either it happens or it doesn't. There's nothing in between, kind of. So because the probabilities sum up to 1, if something has probability p of happening, then automatically it has 1 minus p of not happening. This is like very basic. There are also other types of probabilities such as things like probabilities of many possible things happening. So you could have like p1 chance of something happening, p2 chance of something else happening, etc. And in that case, then like it depends on what you're being asked, basically. But it's sort of kind of doing out the math, I suppose, to figure out the total probability of something. And then at the same time, like the sum of the probabilities is equal to 1. I don't know, I'm not entirely sure what to explain. I think there are probably enough good lectures out there anyway. But yeah, let's see. So I mean, there's that. expected value is a bit more interesting. Like the basic premise of expected value is like, so you have this function e of I, which basically says like the expected value of I or something. And so you can represent the expected value as, face reveal soon. Yeah, you can represent the expected value as sort of the sum of like the probabilities of everything happening. For example, say I is this function which has like a 0.3 chance of being 5, a 0.25 chance of being 7, and the remaining 0.45 chance of being 100. Then, like, the expected value of I is just the sum of the probability of each thing happening times the value you get. So, for example, it would be 5 times 0.3 plus 7 times 0.25 plus 100 times 0.45. And the reason this formula kind of comes about is like you're trying to figure out basically if you did infinite trials of this sort of like random sample thing, what would the average value be? That's kind of what you're interested in. So if you did infinite trials by like some sort of probability law or something, like it would come out to be basically exactly 0.3 of the time you would get 5. So you have, let's say you do n trials, and sort of in a sense let n go to infinity. But say you have a number n, that way we can work with it like a limit. And then basically out of n trials, on average 0.3 of them are going to work out to 5. So we have 0.3 n times 5 in terms of that. And then at the same time, we have 0.25 n times 7, and then we have 0.45 n times 100. Because that's just, we're trying to average these, so first we need to find their sum. And to find their sum, we just take the number of times they occur times the, like the value it has. So we have 0.3 n 5s, therefore we sum all of them up. We have 0.25 n 7s, and then we have 0.45 n 100s. Yeah, 0.25 is 0.25, same thing. So if we do n trials, this is the number we expect to have on average. But then we're looking for their average, so we have to divide by n, because it's the sum over the number, that's what average is, and then we just get this. We get 0.3 times 5, 0.7 times 0.25, or 7 times 0.25, and 100 times 0.45. And in general, this formula comes out to the sum of I times P of I, which is just the probability of I happening. It's just the probability of getting I. Because again, you can sort of think of this, if you want to like think about it mathematically, you can think about it like a limit, and then it will sort of just become this eventually when you go out to infinity. But yeah, that's the basic idea. There's also this thing called linearity of expectation, which is like I think it's like this. I think the formally it goes like this or something. E of I plus j is equal to E of I plus E of j, which means you can compute them independently and then combine them. And somehow this works even if it's not independent. I actually don't get that. But like, yeah, it sort of works even if I and j aren't independent of each other, I suppose. And there's some sort of like mathematical proof for this that just makes it work out. Yes, I is a random variable, but we assume it has some sort of like discrete representation. Otherwise, you'd have to do calculus or something. I don't know. For like, right, E of I plus J. Independent or mutually exclusive. I think it is independence from what I remember. Let me confirm this. Yeah, it is independence. So even if they aren't independent of each other, it's still going to work out somehow. Like for example, say they're like directly related. Like I is equal to like I is equal to, for example, x minus j. Then whatever j is, it's going to uniquely determine x. But the point is, in total, their sum is going to be like we just have this equation I plus j is equal to x, right? And on average, their expected value is going to be, like, for example, some value between 0 and x. Say I is some value between 0 and x, and j is also some value between 0 and x, which makes this equation work. And then their expected value is x over 2 and x over 2, which just, like, works. The expected sum is x, and the expected values are x over 2. So, like, in this case, it works out. I mean, yeah, I can't do a single case, and that won't... Like, a single case isn't a proof, but it's sort of like, this may be the counterexample you're thinking of, but it still ends up working out somehow. If you do, like, multiplication or things, it might... I think it still works. Like, you can have any relation between the variables, and you can still do this sort of thing. What? Okay. In terms of expected value, that's what I know, so I can cover that. Yeah, okay. So, let's see, where are we now? There's also combinatorics, which is like basically counting. Like counting a bunch of different things. For example, counting the number of subarrays that satisfy some property, or counting the number of subsequences that are like increasing or something. A lot of the times, this can be done with, for example, dynamic programming. It's a good way to do it. Although oftentimes there are better formulas, like for example, there are things like the binomial coefficients and choose k, which is the number of ways to pick k objects out of a group of n without ordering and without replacement, I believe. There are also like other tricks you can do, for example, counting the complement, which is to say, instead of counting the number of ways something can happen, count the number of ways that it like can't happen. Or like, is maybe not happening, but like instead of counting the number of ways to have a certain property, count the number of ways to not have that property, I guess. And sometimes that's easier. So, like counting the complement, for example. There are other things too. There's this magical thing called inclusion-exclusion. Yeah, there's this magical thing called inclusion-exclusion, where basically, like for example, like the size of something that's like the number of ways to have either of two things happen can be represented like this. It's the number of ways to have either thing happen minus the number of ways to have them both happen. Which is to say, this is fancy set theory terms for, this is union, that is the it's basically the like sort of like you stick the two sets together, but you get rid of duplicate elements, essentially. So it's basically like the union is like you take all elements that are in either of the sets and possibly both. But the problem is, like for example, say I have one. I'm trying to draw brackets here. 1, 2 union like 1, 3. You won't take the 1 twice, so you end up with 1, 2, 3. So if you add these two together, you're going to get 2 and 2, which is going to be 4, but the problem is you've counted this 1 twice because it's in both sets. Oh, wait, what? But the problem is you've counted this 1 twice because it's in both sets. So that's why you end up subtracting the things that are in both sets. This intersection is this symbol means intersection, and it's basically anything that anything that's in both. So this 1 is in both, but these 2 and 3 are not. So you would basically only subtract the one using both, and then it sort of extends to like any number of elements. For example, like here we have only 2 sets, but say we have like 3 sets. Then like for example, A union B union C ... right? And then it would be like the sum of all 1 element sets minus the sum of all 2 element sets. It'd be like the sum of all 1 element sets, let's call this S1, minus the sum of all 2 element sets because you overcount them. But then once you subtract all these out, you end up undercounting the number of sets that have 3 elements, so S3. And then it's just sort of alternating. Then once you do this, you end up overcounting the number with 4, and it just kind of like works out until you get to n. Yeah, that's that. So it's kind of like quite useful, actually. Comes up a lot, specifically in ACT-coder problems, which I do not think I'm a fan of, but it exists. It's probably important to know. Let's see, what else do we have? We have got... I'll leave it there for now. I think in terms of the mashup, that's all it covers. There's definitely more combo things, like a very broad topic with a lot of different formulas and things, and identities and stuff, which I don't actually know because I haven't really studied combo. So yeah. De Morgan theorem? What is that? Let me look that up. What is this? This is like a different... or De Morgan theorem. It's a different thing? Okay, that's different. I'm not sure what that... I know De Morgan's law, like in Boolean algebra, but that feels different somehow. Okay, anyway. So I guess with that very brief and like not very well explained introduction, just get into the problems. I don't know. So the way this mashup is designed is basically let's see, I have templates. The way this mashup is designed is you have these first 2 problems are designed to be very easy, just 1300s, or relatively easy, I suppose. Then there's these last 3 problems are 2000, and like there's some 1700s and 1800s in this range, the 3rd to the 7th. So okay, the first one's like quite simple. It's technically combinatorics. So I kind of just include it as a freebie, but it is counting. So it's like basically the idea is you have an m by m table. Each cell of the table is colored white or black, either so 0s or 1s. Find the number of non-empty sets of cells. So like take sum of the cells, such that all of the cells have the same color. It's not all the cells have the same color, so they must all have the same number. And every two cells in a set share a row or a column. So what that means is that, say I pick, like for example, something like this. I have to be able to, for every pair of cells, they're either in the same row or the same column. And you want to find the number of such sets. So for example, this is not a valid set because I can take this one and I can take this one and they're not in the same row or the same column. Let's see, n and m are up to 50. So basically the idea is, consider this. Say I have any sort of formulation, or say I have any sort of subset like this. Then there are two cells that are sort of diagonal from each other, and they're on the same row or the same column. And in general, just consider this cell. If I put anything that's not on this row or this column, like for example, if I put something here, it's automatically going to be invalid. So whatever I take next, it has to be on either the same row or the same column. So for example, without loss of generality, I guess, say I take something on the same row. Then now, what has to happen is I have to take something on this row or this column. Can't draw. And I have to take something on this row and this column. But what that means is, like, I can't take anything here because it would be invalid for this one. And I can't take anything here because it would be invalid for this one. So once I have two things, the only thing I can do now is take other elements on the same row. And of course, it goes also for columns. I can do something on the same column and that will work. But in general, the only thing that's possible is that everything in the set is either in the same row or everything in the set is the same column. So now we ask, for a single row, how many sets are there? So for example, say we have X orange cells and we have Y red cells or something. So we have X orange and Y red cells. Well, we can take anything here as long as they're all in the same row. So basically we can take any subset of these four. And the number of subsets is simply 2 to the n, because here you can either take this thing or you can't. And so therefore you have two ways to handle this one. And this one is totally independent from this one. So you have two ways to handle this. You can either take this one or not. But here you could have also taken this one or not. So you have two ways, an additional two ways here. So you sort of like multiply. So you have 4 ways now. And then here you can either take this one or not. So you have 8 ways, another possible like 2. And then here you have another possible 2 ways. So it's 16. And in general, you have 2 to the n ways to pick orange, except you can't have an empty set because that's bad. Like you can't, like one of the possibilities here is that you don't take anything. So you just like don't have any orange cells. But that doesn't really make sense because it has to have something in it. It specifically says non-empty sets. So here we have to subtract 1 because we have to have something. And in the same regard, for y, we have, or this shouldn't be 2 to the n, this should be 2 to the x, to keep with my own terminology. And here we have the same idea. We have 2 to the y minus 1 ways to pick red things. And that's basically it for a row and a column. The other problem is that n, or like x of these sets, are going to only contain one element. Specifically, we can only have the first element, we can only have the second, we can only have the third, and we can only have the fourth. But the problem is that it's going to, if we consider columns the same way now, we're going to count this one twice. One for counting in column-wise, and the other for counting in row-wise. So each set that contains a single element is going to be counted twice, which means that in the end, we have to subtract the number of elements we get, which is just n times m. So it's this idea of being careful to first only count the right things, and second, if you do overcount, you can sort of subtract stuff later to compensate for it. So essentially for each, let's just solve for each row first and then solve for each column separately, and then we subtract out an m because each individual set is counted twice. Once for row, once for column. So let's do that. So first create the matrix, just like read in the thing. Now, for each rows, like let's do it row-wise. I'll be consistent with my own notation here. X will be the number of zeros, Y will be the number of ones. It's easier to use an array, but like whatever. Wait, that's what you were doing? That's why you were doing 50 choose 25? Nice. That's very smart. That's very smart. Yeah. I mean, you can also think of it like sort of combinatorics, like you can think of it as the number of ways to pick one element from 4 things, and the number of ways to also pick 2 elements, and then 3, and then 4, but it sums the 2 to the end because it's a polynomial. That's basically the way it works. I may go into that more detail later, but it's not really important right now. So if right now we're just counting the number of ways to have zeros and ones, then one of the possibilities is that we take only orange ones. So we want 2 to the x minus 1, and the fancy bitwise trick to do this is to just say, basically, we take a 1 in binary representation, which is initially a 1, and then for like x times, we sort of shift it over. So for example, if we wanted 2 to the 3, we would shift this 1 over 3 times. And then we would get a number 0, 1, 0, 0, 0. And notice that every shift is equivalent to multiplying it by 2, because in binary, every next digit is worth exactly twice as much as the previous one. So to quickly compute a power of 2, we can simply just do this sort of binary shift. And this operator, this bit shift, is exactly what we want. It will shift this 1 over by x bits, which gives us 2 to the x. And we do the same thing for y. And then in total, we print the answer, but we have to subtract out n times m because we overcounted. See, I'm still recording it. Yep. Sanity check, as always. So we get 0. Nice. Because I haven't actually done columns, that's why. So for each column, for each row, so now we do it for columns. For each column, then for each row in this column, we count the same thing. No. 1, 8. Okay. Let's see, that's not going to overflow, right? Because I'm using long specifically. And n and m are up to 50, so the powers of 2 are going to be small. Sweet. We subtract n times m because if we consider these columns and these rows separately, notice that we have this sort of intersection at this point. And then this point, we're going to count the set that contains only this point twice. Once in the column direction, once in the row direction. So to compensate for that, I subtract out n times m because that's exactly the number of things that are overcounted, the number of cells in the grid. Oh, I forgot. Oh, God, I keep forgetting to put the pins down. I keep forgetting to pin the message that says what I'm doing. Wait, I am a manager still. That's annoying. Wait, you guys can't see this, can you? I thought I disabled it, but I guess I didn't. Okay, let me try that again. Wait, am I like even on the leaderboard at this point, or no, I'm just not? Okay. Okay, yeah, there we go. That should work. Alright, so now I'm gonna actually pin the message now, because that's a good idea. So current problem is B. Nope. I don't know what hotkey I just did, but that was not right. This works, right? Like you can see this link. I would hope so. That'd be annoying if you couldn't. Right, okay. B, archer. Small r is an archer. Small r is taking a match of archer with the nose. Sure. They try to shoot in the target in turn. I'm sure there's a better way to pronounce that, but whatever. They try to shoot in the target in turns, and small r shoots first. The probability of shooting the target each time is a over b for small r, while it's c over d for the nose. The one who shoots in the target first should be the winner. I'll put the probability that small r will win the match. Okay. Now, here is the fundamental, well, not fundamental, but I mean, it's one of the big ideas of probability. It's just math. And like, here's where this sort of comes in. Let's define this function, let's define this, or let's say this value, let's define this value p. And let p be the probability of small r winning. We want to find some sort of equation for p. So the first thing that happens is small r shoots. So with probability a over b, he wins. Or like, for example, okay, initially you have probability 1. Like, it's just, like, you have one, well, I mean, how would I put this? Like, you have, like, obviously you start in the beginning with 100% chance of starting in the beginning because there's no, like, probability that's happened yet. You just start with 1 as a baseline. Now, let's sort of think about this like branching. So with probability A over B, actually I'll put it on the branch. With probability A over B, you win. And that's it. Otherwise, with probability 1 minus A over B, because that's the chance of you not winning, then it continues. So now with probability C over D, your opponent will win. So therefore you lose. And with probability 1 minus C over D, you continue. Right? So here you have an A over B chance of getting here, and otherwise you have the remaining 1 minus A over B chance of getting here. Then once you get here, you have a C over D chance of getting here, and a 1 minus C over D chance of continuing. So there are 4 possibilities, and they all lead to different outcomes. But to get to here, what's the probability of actually getting here? Well, first you have to have done this thing, this 1 minus A over B chance, and then you also have to have done this C over D chance. So the probability of getting here in total is 1 minus A over B times C over D. And the probability of getting here is the probability of doing both of these, which is, oh yeah, this is a property of probability, that the probability of two independent things both happening is their product. Because essentially, I cannot draw B. Yeah, it's just their product because, like, both of them have to happen. Like, say you have a 0.5 chance of this and a 0.2 chance of this. Well, like, first the 0.5 chance has to happen. And then, along with that, the 0.2 chance has to happen. And the probability of both of them happening is, like, you have a 0.5 chance of coming here, and then once you do, within that 0.5 chance, you have a 0.2 chance of this happening. So it would just be their product. Because it's like, it's 0.2 chance of this space, which is already 0.5. Yeah, and like there are other probability rules too. Sure. No, this should be lose because this is your opponent winning. You don't want that. All right. So in general, we have an A over B chance of winning. We have an A over B chance of winning. We have a 1 minus A over B C over D chance of losing. And we have 1 minus A over B 1 minus C over D of continuing. So how do we represent this as an expression? Well, what we can sort of do is we can think about it like, imagine winning as the value 1, and then losing as the value 0. Then we're interested in the probability of getting a 1, which is sort of the expected score we get. So we can tie this into expected value. And the reason that's nice is because expected value, again, is the sum of I times the probability of I happening. So for example, we have an A over B chance of winning. So we have A over B times 1. And then we also have a 1 minus A over B chance of something else happening. All right, let's say, I shouldn't call this P anymore. I should call this like E of expected value of score. Would that be S? So we have a 1 minus A over B chance of something else happening. So first, in here, we have a C over D chance of nothing. And then we have a 1 minus C over D chance of continuing the game. But what does that mean in terms of expected value? Well, let me move this down. What does it mean in terms of expected value? Well, basically we just reset. Like it's our turn again and nothing's changed. So we're playing the exact same game after 2 turns happen. Which means that we have the exact same score. Well, we have the exact same expected score once 2 turns go by. So the expected score from having neither person win is the expected score of the whole game because it's the same game. So that's to say that briefly, this is also E of S. So now we have an equation, we can solve this. So we have E of S is equal to A over B times 1 plus 1 minus A over B 1 minus C over D times E of S. So what that means is that when we solve for E of S, we get E of S minus this thing, because we just moved this over, minus 1 minus A over B 1 minus C over D times E of S is equal to A over B. Then we just like combine like terms. So we get E of S. I'm being very thorough here, even though it's like not necessary. E of S times 1 minus this whole thing is equal to A over B. And then, so we just solve for this now. So A over B over this whole thing. I can extend this line out, it's fine. It's a bit off-center, but it's fine. All right, so what did I just do here? So first, I figured out the probability of everything happening. Because we have an A over B chance of winning, we have an 1 minus A over B times C over D chance of losing, and we have this chance of just continuing the game. And continuing, again, is the same as just starting the game normally because nothing changes after 2 turns go by. So instead of trying to find the probability, because it's a game and it's zero sum, we can instead try to find the expected score. And that makes it nice because then we can sort of sum up these values, the value of I times the probability of I occurring. So winning is 1, losing is 0, and continuing, if I sort of write this now, it's the same game, so it's still E of S. And therefore, the chances are A over B chance of winning, otherwise 1 minus A over B times C over D chance of getting 0, and otherwise 1 minus A over B times 1 minus C over D times the expected value of continuing the game, which is just the expected value of the game. And then from there, simply we have this equation, we just solve for E of S, because it's a number, and then we're done. Because again, this is math. We're just working with equations here at this point. Zero sum is essentially like there's no sort of like either someone wins or someone loses, or like there's a draw or something. Like basically the sum of the scores is like 1. That is, everything the first player gains, the second player loses, kind of. Let's see. Yeah. Geometric sum. Yeah, that works too. Oh, S is just this variable I made up. It's just basically score. Like, it's the expected value of the score. I think that might actually, it might actually be wrong notation to say it like that, but like whatever. It's just the expected value of the score. Yeah, so there's also this geometric series sort of thing where you can sort of just analyze it and also do a similar sort of math bash. So the probability of winning is you have A over B in the first turn. And then to continue, you have to have 1 minus A over B, 1 minus C over D, chance of continuing the game. And then once you get here, you have another A over B chance of winning. And then if you don't win here, then you have sort of another, like, you have to get through another 1 minus A over B, 1 minus C over D chance, which is to say, it's 1 minus A over B, 1 minus C over D squared, because you have to have gotten through here the first time, and then after you got here again, you have to go through the second time. So you have, like, the multiplication rule, basically. You have that squared chance. And then once you get here, you have another A over B chance of winning, and it sort of just goes on. That this number goes into higher and higher and higher powers. So essentially, let's let this number be R, because that's the notation we want. So let R equals 1 minus A over B, 1 minus C over D. And furthermore, we can also do some more notation. And we can say, call this number P. Let P equals A over B. Then we basically get this number. So A over B. No, wait, I just violated my own notation like immediately. So we get P plus R times P plus R squared times P plus R cubed times P, and etc. And this is what a geometric series is, or sequence series. Yeah, it's the sum of an infinite number of terms, which means we can apply this formula that just works for geometric series. It's the initial term, which is P, times or divided by 1 minus the common ratio, or R. And if you plug it in, you'll get the exact same formula. So it just works. So, like from there, once we derive this whole formula, the code is like insanely simple. We just print it. So, let's see. Long double A, B, C, D. what this does is we're going to use this a lot probably. So what this does is it basically makes it so instead of, so what this does is it means it's never going to print scientific notation, which is very good because that is a very subtle way to get wrong answer. That you'll print something like 1.7E10, which most checkers won't recognize as a number. So even if it's correct, it'll be wrong because it's a string. So you do this fix to make it not print scientific notation. And set precision basically means that it'll print 10 decimal points, like for example what they're doing here. I think they actually have 12. Yeah, I'll be consistent with them. So set precision 12, and then now we just do this formula. So C out A over B divided by 1 minus A over B times 1 minus C over D. Yeah. So derive a formula, make it work. This is the sort of ad hoc thing that people don't like in like code forces anymore, because it's like all the thinking is on paper and then you have like this one-line program basically. So we have this problem now. Yeah. Okay. So now we're getting to C, and at this point, as you can see from the solves, I'm sure the difficulty is like spiking by now. So this is the first 1700 problem, and it's like not the greatest. I mean, it's like let's see. I mean, not the greatest. I would say like I shouldn't have to repeat. You can rewind the stream if you want. Okay, basically set precision will make it so set precision 12 will make it so you print 12 decimal places. So for example, I printed 12 things. If I have this set to 100, or yeah, 100, then it'll print 100 decimal places, which is like insane because there's not even that much precision, but that's basically what it does. And then this fixed makes it so I won't print scientific notation. So for example, if I don't have fixed here, 0.0. If I don't have fixed here, then what's going to happen is, actually if I make this, the default precision is 6. So if I don't have this at all actually, I'm like 1, 2, 1, 2. Oh wait, that does work. There's some way to like make it not work, I think. Like eventually, somehow it'll start printing scientific notation. Wait, I should figure this out. I know it does this eventually. Maybe on other compilers, I guess. Like if I do this on code forces, it might. Yeah, I know about the pin. I'll remember. Let's see. So 1, 2, 1, 2. Okay, I guess not. Wait. Stick some more numbers in. Okay, I guess this is not doing it. But on some compilers it does. I've had this problem myself before, where instead of like, it's just kind of like being weird and in scientific notation. Okay, I've forgotten to do multiple things. I also have to update the subscriber count. Like I haven't done that yet, which is kind of sad. But now I will. Perfect. So I'll do that, and at the same time I'll update the pin message. Oh yeah, I didn't actually pin it. I always like manage to do that somehow. I send the message and then I just don't. Yeah, maybe something like this, like 100. What? Okay, you know what? Oh wait, it's because I have this. It's because I did it before. Okay. I'm being dumb because my own template does this. Yeah, you see, now it'll print 1e plus 100. Yeah, okay, I'm being stupid. I had this before. So, okay. Well, in general, it's a good it's a good idea to do this anyway. So, in a sense, it's a good thing that I like. It's a good thing that I accidentally did this because it's a pretty good idea to have this in your template anyway. There's no reason to not print fixed numbers. Or maybe there is for debugging, but like, I'm really glad you can't clip things on YouTube. Oh my god. Okay, right, so if I do this now, it'll, actually it'll print as an integer, 0.0. Okay, but now I get rid of it, and then yeah, there we go. Okay, finally. The long struggle. Okay, anyway, let's get into problem C. I pinned the right message, right? Yeah, C. Okay, you're given an array A consisting of n integers. I've already read it, I'm just reading out loud. Let's denote the monotonic renumeration of array A as an array B consisting of n integers, such that all the following conditions are met. B1 equals 0. For every pair of indices ij, if their values in A are the same, then their values in B are also the same. Which doesn't necessarily imply that different A values have to have different B values. And for every index I, either for every like consecutive pair of indices, this is either 0 apart or 1 apart, which means you can't go up by more than 1. And so for, as they give an example, so 1, 2, 1, 2, 3, the possible monotonic renumerations, and the only possible ones are 0, 0, 0, 0, 0, and 0, 0, 0, 0, 1. You want to calculate the different number of these, or the number of different ones. And you want to take it modulo this number. So this is a commonly occurring theme. Modular arithmetic, you want to find the number of ways modulo some big number. And basically modulo is the remainder of division of a number by this. And the cool thing about modulo is that you can do things in any order. Like for example, A plus B mod M is equal to A mod M plus B mod M mod M. So therefore, if you do mod like along the way, you'll still get the right answer. Which means that you can moderate it, so mod, yeah. So all these numbers are less than this number when you do operations with them. So it doesn't overflow, that's the point. The point is to have it not overflow. Right, okay. A bit of intuition. Look at these samples. All these answers are powers of 2. Maybe that helps. I don't know. Maybe it does. Just a slight trick you can use. Although sometimes samples can be misleading, so don't like take it for granted, but it could suggest something that you might later want to verify. Everything is a power of 2. Interesting. And indeed, I will show why that is important. Let's get rid of all this first. Wow, that's a lot of math. Yeah, it just is a math problem on Code Forces. Right, so take some array, for example, 1, 2, 1, 2, 3. Notice that first this value has to be 0, because that's the constraint of the problem. This value has to be 0. Then, notice something, that this 1 over here also has to be 0, because if it isn't, then we have two elements that have equal values in A, but they don't have equal values in B, and that's a problem, because that violates a condition. So once we set this value, every value that's equal to it in the array is the same. Like, it has to be the same, which means that once we set this value, we automatically know that this has to be 0. Okay, but now think about the constraint we have. Either bi plus 1 is equal to 1 plus bi, or bi plus 1 is equal to bi. But what that means is bi plus 1 is greater than or equal to bi. So every element ahead of something is going to be at least as large as everything before it. So yeah, what this means is that since we have this 0 here, the 2 here before it also has to be 0, because there's nothing else we can do. Like, it has to be 0, otherwise it'll be too big and we'll never be able to go down again. So now that we have this is also constrained to be 0. And again, we apply the same thing. We have a 2 later on, so this 2 has to be 0. So 4 elements of the array, just from the beginning, are fixed. And therefore, the only possibility is to have this 3. And we have no constraints on this 3 whatsoever. It can be 0 because it can, or it can be 1 also because it can. Because like both of these cases are possible because we have no constraint on 3. So in total, we have 2 ways, because the 3 is the only thing that has multiple ways. Let's consider some other case. For example, let's take a bigger array. So we have 1, 1, 2, 3, 2, 3, and 4, 4. Notice that this has to be 0 again, so we do this. And once we do this, this has to be 0, because it's fixed. Then this can be either 0 or 1. I'm intentionally using a different color. This can be 0 or 1, but then that fixes this to be whatever this is, so it's the same cyan. Then this 3 has to be whatever this is, because it's between 2 cyan elements. And then this 3 also has to be the same as this. So we have this sort of group of elements that have to be the same. And then over here, 4s are kind of independent from the rest of these, so this can be orange, and then this other 4 also has to be orange. So in a sense, we have 3 groups that are completely independent of each other. All of these elements have to be the same, all of these elements have to be the same, all of these elements have to be the same, and all these elements have to be the same. But whatever these elements may be, we can sort of make them whatever we want. So this one has to be 0. Then this one can either be 0 or it can be 1, just based on the constraint. This can be 0 or 1, or this can be 1 or 2. But notice that there's never any overlap. Even though these ones are the same, because they come from different values and previous values, they're not going to be equivalent. So therefore, we can count them separately. And in general, every time we get a new group, we have like an extra 2 possibilities. Like for each other possibility, we have 2 branches, which means that the total number of the total number of possibilities we have is multiplied by 2. Because each possibility has 2 separate possibilities for this group. So the answer in general would be 2 to the number of groups minus 1. Because each group, except for the first one, gives us 2 possible options. So yeah, powers of 2. As I said, reading samples, even if it doesn't give you the answer, it can give you some sort of intuition about what it can be. And especially for constructive problems, you can try to frame a constructive algorithm based on what they do in the samples. It's not always going to work. It's just sort of to help you. Because again, when you're solving problems, it's mostly trying random things and seeing what works, right? So if you look at the samples, that's the best sort of thing you can look at to think of the best random things to start with, you know? So it can't hurt. So it remains to find what the groups are. And how do we do that? Well, yeah, samples can be misleading, that's true. So you should not blindly trust samples. But what you can do is, whatever your normal thought process is, combine it with samples, and it will sort of give you, it can sort of give you inspiration for the answer, maybe. It's just a possibility. So now we need to find the number of groups. Note that in this array, the groups are sort of contiguous and they're separate from each other. And in general, this will be true. Because the very formation of the groups requires this. Say we have some 2. Or say we have some element here. This should be a minus 1 here. And then say we have some other element here. And then imagine, for purposes of contradiction, we have this group here. But then this doesn't have to be equal. But, it does. Or say, imagine for purposes of contradiction, we have 2 disjoint groups. But then, everything here, because it's monotonic, it has to be less than or equal to this. And it has to be less than or equal to this. And these are the same. So this also has to be the same. That's the only possibility. And so basically, groups are going to be contiguous. Because if they're ever not, then it will sort of fill in the gap by this sort of argument. So because it's contiguous, we can imagine we're in the first group to begin with, and then we can sort of find the ending position of this first group. And how do we do that? Well, the ending position will be, like, whatever our starting element is, if it's equal to some element later on, then everything in this range has to be equal to it. But then some elements in this might also be equal to something later on. For example, this 3 is equal to this 3. So we sort of extend this group out. Even though this isn't true for this sample, we sort of extend this group out until we don't have any more equalities sort of in the future. So how to put this? How do you explain this? That is the question. So basically, the strategy would be to sort of sweep through the array, I suppose. So sweep through the array. At every point, we maintain the position of our the end of our current group. So for example, we'd be here, and we have this 1. But we know this 1 is equal to this 1, which means that actually this current group can't end here. It has to end later, specifically over here, because we now know that this has to be equal to this. So now we sort of move this pointer over here, and well, this 1 is not equal to anything, which means that all of these elements have nothing to do with this group. So this group is done here. So we found a group here. So we found the blue group. Then let's continue. Now we move both of these over, both the pointer and the current position. Now we know that this 2 has to be equal to this other 2. So therefore the end of this group has to be over here, because again, groups are contiguous, and we know that the group ends at least over here because we have this equality. So now we move on. We have not found the end of another group yet. We have this 3. This 3 has to be over here. So that means that the end of this group has to actually be by the end of this 3. We continue. This 2 has no more equalities. This 3 has no more equalities. So we found the end of the group here. So now we have a second group. And then we're here. Then we have this 4 that's equal to this other 4, so we move the end once again. And then at the end of the array, we finally get the final group. So in total, we count 3 groups, and we do this by sort of 2-pointering and maintaining the end of the current group we have. And at every point, we set the end of the current group to the maximum of itself, because it has to be like either to the right or the same. And at the same time, we set it to the maximum of that and the last position of the current element. Not necessarily the next one, but the farthest in the array it is. Because what that means is that sort of everything will be because everything in the range from the first position of the 3 to the last position of the 3 has to be the same. So it's sort of, we know that the end of the group has to be at least here. And it could be farther, which is why we take the maximum, but it has to be at least here. And it sort of gives no other constraints. So that's why we can do this. Because we're just checking like all of the possible constraints for this group. So let us see. At this point, we write the code. And it turns out to be very simple. Let's just we'll basically use a map to keep track of the last position of any element. I think nlog n is, yeah, I mean, it's fine. Not sure there's an easy way to do an O of n. Doesn't really matter. So group end is equal to 0. And then n groups is equal to or I guess 0. Yeah, we start off with 0 groups. Then, let's see. So, once again, at every point we set the current ending of the group to the maximum of itself and the last position of this element, because we have the constraint. And this is sort of, okay, so in terms of combinatorics, like it's not exactly like the sort of math bashy formula you would expect, but it is still definitely counting. And it's still like this sort of formula that everything is sort of independent of each other, so you just like take a power of 2. So let's see, if the group ends at the current position, if the group ends, yeah, at the current position, then we found the end of a group. So then we mark a new group, and we increment the number of groups because we just found one. And then we take 2 to the number of groups minus 1. We have to do it modulo, so n groups minus 1. Could do this with binary exponentiation, but it's not that big a deal because no matter what, the number of groups is at most n, so this won't do that much work. Some wind going on, it's kind of fun. We get 2, 2, 4, and again in this example we would have 2 groups because we have 1, 3, 3, and 7. And in fact we can test it with this sample I made. So we have 8, 1, 1, 2, 3, 2, 3, 4, 4, and we should get 4, which we do. And yeah, that's basically it. Okay. Yeah, my sneaky observation paid off. Interesting. Yeah, no spoilers is generally a good thing, just for other people as well. Yeah, smallest and large. What the hell? 343? Why that? Is STL really that bad? I don't remember it being that bad. Yeah, smallest and largest intersection is exactly what this is, or smallest and largest index is exactly what this is. I don't, wait, okay, I guess STL just is that bad. Wow. Fun. Okay, and now we're in 3 problems. This is not bad pace. So let's continue. I will remember to do the pin this time, as I usually don't. So, why did I submit C++17? Oh, because usually I do use C++17 with 64-bit, but I like forgot that I set it to 14, so I just changed it back. Like, this is what I would normally do, I just had it set to something else for some reason. Alright, there are n sharks who grow flowers for what shark? They are all sitting around the table, such that sharks I and I plus 1 are neighbors for all I from 1 to n minus 1. So you just, okay. Sharks n and 1 are neighbors too. Each shark will grow some number, so they're in a circle, right? Each shark will grow some number of flowers Si. For the ith shark, Si is a random integer equal probably chosen in range, nice, yeah, in the range from Li to Ri. What shark has its favorite prime number P, and he really likes it? If for any pair of neighboring sharks I and J, the product Si times Sj is divisible by P, then what shark becomes happy and gives $1,000 to each of these sharks? At the end of the day, sharks sum all the money what shark granted to them. Find the expectation of this value. So we're looking for the expected total number of money of each of the sharks. So let's see. Mathematically, sort of with a formula, let E of I be the expected value of money. Let's see. I won't use the dollar sign because that's not like universal. Of money of the ith shark. Right. And then the answer we're looking for is the sum of EI. Note that this works because even though we're technically looking for okay, actually, I guess I should make this a variable because EI could just technically be the expected value of the index, which is not exactly what we want. So let's let MI be the money that the ice shark has. Then the expected value of MI is just the expected value of each shark's money. Note that while the actual answer is the expected value of the sum, which is to say M1 plus M2 plus M3 plus ... to n, we can represent it as this because we can represent it as this formula, the sum of each individual shark's money, because of linearity of expectation. So therefore, we just need to find in each individual shark's money. Now, how do we do that? So each shark has two neighbors. Each shark has two neighbors. We can consider them independently because each neighbor is sort of like chosen separately. So let's consider this shark, and then it has two neighbors. It has one to its left and one to its right. And we sort of have to solve for this. Although consider the fact that we actually no, I'll leave it like this for now. So we're interested in, let's consider just one pair of neighbors. So for example, we're solving for this shark and some other shark. Then we can solve like independently for these two and also for these two. Yeah, this problem is D. I think the pin should be right. I don't know, I kind of forget to do it often, so who knows. Yeah, we're on D right now though. So we're interested in the probability of this pair getting $1,000. So therefore, this shark will get $1,000 from it. So this shark has some value, L1, R1, and this other shark has some value, L2, R2. We're interested in the probability that their product is P, where P is specifically a prime number. That's important, because it means that it has no prime factors. So there's no way to choose some x and some y such that x times y is a multiple of p, which means p divides x times y. But at the same time, like, p doesn't divide x and p doesn't divide y. It's not possible for this to happen. P being prime implies that if p divides their product, it must divide at least one of them, because it's just prime. It has no factors. So p itself must be one of the factors of something. So now we're interested in the probability that p divides x or p divides y, which is the same as saying, like, the yeah, it's the probability that, like, okay, how do I? The problem is I'm repeating p twice, and that's kind of annoying. So let what variable do I use? Let a be the probability of p dividing x, and b be the probability of p dividing y. Actually, let's use better notation. What do I do? What P sub x, so the probability of P dividing x, that kind of makes sense. And then P sub y be the probability of P dividing y. And this like bar symbol, it just means that like this thing on the left divides this thing on the right. So this thing is divisible by P. So we're interested in the probability of this is not the value P. It's the probability of A or B. Which is the same as saying, if we consider A and B as independent sets, then we're interested in the probability of A union B, which is a formula we've seen before, and in fact, we can compute this by doing inclusion-exclusion. It's the probability of A plus the probability of B minus the probability of PA intersection B, which means both A and B are occurring at the same time. This is also PA and B. Right, so this is simply P sub x. This is simply P sub y. And what is this? Well, A and B are completely independent of each other. Our choice for x and our choice for y don't depend on each other. Which means that the probability for A and B happening is individually the probability of x being divisible by P times the probability of y being divisible by P because they're independent events. So therefore we get P sub x plus P sub y minus P sub xy. No. P sub x times P sub y. Because it's like they're independent. That's just how it works. So this is the probability of that. There's also another way to do this, and specifically we can say wrong color. We can specifically find the number of ways to have this not happen. To have, for example, we can find the number of ways to have this not be true, or to have this be true, that both x is not divisible by P and y is not divisible by P. Because, like, sort of we have four cases. We have both A and B. We have A but not B. We have not A but B. And we have not A and not B. And this is this case that neither of them are true. We're trying to find the probability that at least one of them are true, which encompasses this whole thing. Everything except for the case where neither of them are true. So that's kind of cool, right? Because we know, just based on how probability works, probabilities sum to 1. And we can find this by multiplying, because again, these are independent events, so we can multiply this and this together. It's just the probability of two separate things happening. So this we can find. And then we can find green, instead of doing an inclusion-exclusion, we can represent this as simply 1 minus the cyan. This is a really interesting equation. So green square equals red 1 minus cyan square. All right? So in sort of probability sort of equation type things, we have probability of A or B, A union B, is equal to 1 minus the probability of, like, not A, this is sort of a not symbol, and not B. Which is easier to find, because this is independent, so we multiply them. Anyway, that is long-winded. So, basically, this is the probability of it being true. So, if we can find this value, then we simply, the expected value is just the probability of 1 plus the probability It's just the probability of 1 times whatever you get for 1. And specifically, the expected gain from this pair is like the probability of getting 1,000 times 1,000 plus the probability of getting 0 times 0. And obviously this just dies because it's 0. So the probability of getting 1,000 we've derived is just this. This is the probability of either of the numbers being divisible by p, which implies that the product is divisible by p. So how do we find this? Well, we can find px and py individually. Each number has a probability of being in a range Li to Ri. So let's find px on a range Lx to Rx, maybe. We're basically interested in how many multiples of p do we have on this interval. Now we can do this with math, but there's like a quite elegant way to sort of think about this. It's very easy to find the number. It's very easy to find the number of multiples of p on a range starting with 1. It's simply the floor of Rx over p. Because after we have the first p numbers, we get 1. After we have the next p numbers, we have 2. But we have to sort of complete the whole range before we get this. So it's sort of the largest x. So dot dot dot. It's the largest x such that x times p is less than or equal to Rx, for example. And like this is just the definition of floor. We're looking for x, so we say x is equal to so x is less than or equal to Rx over p. X has to be an integer. So this is just the definition of floor division. The greatest integer such that xp is less than or equal to a number. But then like this is overcounting because we have like this extra range that we don't want. But we can also find it for another value. Specifically, we can find it for 1 and Lx minus 1. I'm going to capitalize L. And what that means is that I've drawn this diagram many times now, but we have this range 1 to R, and we have this other range 1 to L minus 1. And therefore, if we subtract these two, the range we end up with is L to R, which is just what we want. So we're interested in the number of multiples of P in the range 1 to Rx minus the number of multiples of P in the range 1 to Lx minus 1, which is simply this, and also simply Lx minus 1 divided by P, floor division. So that gives us Px, again, the probability of the value x being divisible by P. And then we do the same thing for y, and we find this formula. So we sort of like recursively delve into like solving easier and easier subproblems until we finally get to just this formula. Notice that for this pair, kind of, we're going to consider it twice. First from the perspective of this one, and then later from the perspective of this one. So in total, for each pair of sharks, we consider them, sharks, right? Yeah. For each pair of sharks, we consider it twice. So we might as well, instead of considering each shark individually, we sort of consider each pair as a whole, and then every value be multiplied by 2, so we get 2,000 for like this probability, and 0 for anything else. So then we only have pairs to deal with, which means we don't have to like do things twice, I guess. It may be easier to implement. So now let's just like do this. So read into n into p, then actually, let's be more explicit for the purposes of clarity. Yeah, so first, we're going to consider some arbitrary pair. So for, let's see, LD ants equals 0, long double because it's expected value. J is equal to the next index, which is essentially if we're anywhere that's not the, to find the next index, if we're anywhere not at the end of the circle, then the next index is going to be the next one. And if we're at the end of the circle, then we want the first index to be that. And essentially we can take, like we have n minus 1 here, so if we go to n, then we can take this index mod n, which is 0, and then we'll get what we want. So sort of to find the next index, we can just take I plus 1 mod n. A slight trick. Now we solve for this. Alright, and the way to do that is to, let's see. So, px is equal to wait, okay. How would I do this? Okay, wait, so this is actually, no, this is slightly wrong. This is the number of values that are divisible by p. And the, like, the probability itself is going to be, like, this divided by the number of values we can have in total, which is Rx minus Lx plus 1. I think, wait. Yes, plus 1. So the expression we get is Rx minus Lx plus 1. That's the actual that's the actual value of Px. Yeah, so let's see. Here we get RBI over P minus LBI minus 1 over P divided by RBI minus LBI plus 1. Let me do the same thing for Y. So it's like the same thing, except we just have J everywhere. So right bound of J, left bound of J, right bound of J, left bound of J. Px minus Py, alright, now Px plus Py times minus Px times Py. That's again this formula that we get from inclusion exclusion. Yeah, I have LOD to just be long double. I don't know why I have 2 L's, it doesn't really make sense, I'm just used to it by now, so it's whatever. The standard thing to use is LD for long double, but like I'm lazy. So from here we have this chance of getting 2000, and we have everything else chance of getting 0, so we're only interested in this chance. So that's essentially that. I think that should be right. Want to make sure specifically that's long, because we want this to be floor division. But we make this to be like double division. Yep, so we have 4500. Here we have no chance whatsoever, because nothing will ever be divisible by p. Let's see, I'm pretty sure it won't overflow. Hope it won't. Ideally it wouldn't. I don't think it will though. Because it's just division. Looks good. So a lot of these are sort of just math problems in disguise, and the code ends up being really simple. Like, oh, what? You get wrong answer on test 80 or something? Okay. So like basically we just like the CS topic is linearity of expectation, which means that we can solve for an individual pair. And solving for an individual pair is just a math problem basically. We find the probability and stuff. So this is the subset of competitive programming that is just math. But yeah, in summary, we solve for each pair. We're interested in the probability of getting money for a pair, which is to say this probability will give you 2,000 if you do get money, because it's 1,000 for each of them, and 0 if anything else. So now we become interested in the probability of either the first number is divisible by p or the second number is, which we can compute with inclusion-exclusion. And this is the probability of x, the first number being divisible by p, and the second number, which we can compute using this formula, which we derive from just like the number of ways to have a number divisible by p in a range. So in total, we get the formula, which is essentially expected value of the money is sort of the sum of like this value times 2,000, because that's how much we get for each individual thing. Yeah, sort of just formula bash. Fun stuff. Okay. Any good resource to learn combinatorics? I'm not sure. I'm sure there are good lectures online for like individual topics. I haven't like made an effort to learn it myself, so I wouldn't know. Let's see. The last problem was the task that Lior's left after sweep pulling class. Yeah, that would make sense. It's not like it's not it's an interesting problem to say the least. I don't think it's that bad in terms of implementation though. Although who knows? Anyway, so we have E now. I'm pretty sure this is another sort of probability thing. Copy this once again. Send that into chat and continue. Okay. Ilya got tired of sports programming, left university, and got a job in the subway. He was given the task to determine the escalator load factor. Let's assume that n people stand in the queue for an escalator. At every second, one of the two following possibilities take place. Either the first person in the queue enters the escalator with probability p, or he doesn't move, paralyzed by his fear of escalators and making the whole queue wait behind him. Formally speaking, the ith person in the queue cannot enter the escalator until people with indices from 1 to I-1 inclusive enter it. In 1 second, only one person can enter the escalator. The escalator is infinite, so if a person enters it, he never leaves it. That is, he will be standing on the escalator at any following second. Ilya needs to count the expected value of the number of people standing on the escalator after t seconds. Your task is to help him solve this complicated task. N and t are up to 2,000. Probabilities are up to 1, obviously. Numbers n and t are integers. Number p is real, given with exactly 2 digits after the decimal point. Okay. Anyway, so we have a thing here that's like, right? We're interested in this expected value of n, which is to say n being the number. Actually, I shouldn't use n. Let's call it the expected value of c. This is going to be a bit hard. C is count of people on escalator. Not number, count. So I can call it C. Now, how do we find this? So, we're essentially interested in, well, actually, wait. So, like, this in itself kind of, like, sucks. It's just not that useful. What we need to do is break it up into the individual possibilities, like the formula. So, what is E of C? Well, we have a certain chance of having exactly one person. So, the probability of having one times, okay, wait, I need to be careful. I need to be careful with my notation. Let Qi be probability of having I people on the escalator in the end. Alright, so let Qi be the probability of having I people. So, the answer would be Q1 times 1, having one person, plus Q2, probability of having two people, times 2, plus Q3 times 3, etc. This is just the expected value formula. So the probability of having I people times the value of I itself. How do we find a specific value of Qi? That is the question. Well, it has to be after t seconds, after t seconds, at least the first I people have to be on it. It doesn't matter if we have more. Actually, it doesn't. Let's see. That's a good question, actually. Does it matter if we have more? What's the probability of having exactly? Actually, I think it shouldn't be at least. I think it should be exactly. That's kind of important. That's kind of an important distinction, actually. So after t seconds, we have exactly only the first I people. Right, now how do we do this? Well, first notice the constraints. N and t are small, which is nice. Which means this an O of nt solution can work. Now we can do this with combinatorics, I believe, but it's also just like a good idea to not. Actually, we might not even be able to do it with combinatorics. Let's just like not try to. What we're interested in happening is after t seconds, like we need to solve this for all I. Notice that like at any point in time, the only thing we care about is the current person we're on and the amount of seconds that have passed. So if all we care about are the number of people and the current amount of seconds, like this is a small possible, we have a small possible number of values for this pair. So why don't we do some sort of like brute force or some sort of optimized brute force to figure out what this is, which is, in other words, dynamic. I don't know how to segue into this, but in other words, it's dynamic programming. That's the point. You can say that you let dp of n and t to be probability of having exactly n people on the escalator after t seconds. This is nice because the only thing that matters is this and this. So once we do this, at a certain state, there are only two possibilities. Either the current person, which we know because that's in the state, is enters the escalator. So then we have a probability of p plus 1. No, what? P plus 1 doesn't make any sense. We have probability of Pn, which goes to dp of n plus 1, because we have another person now, t plus 1. And otherwise, we have probability of 1 minus Pn, just the other possible case, which goes to dp of n, the same amount of people, and t plus 1. So, p of n. Right, so in a sense, from this state, if we go forward, then this state gains Pn times this. And otherwise, if we don't go forward, this state gains 1 minus Pn times this. So we can sort of reverse the formula, but I still like to think about it like we sort of push this value out to further states. We add this value to the states that it contributes to. So we would add Pn times this to this value. And then we would add 1 minus Pn times this to this value, because that's the probability of sort of coming from this state to that one. So it's sort of like pushing this state out to further ones. That's why I call it push dp. Right. So from here, then the answer is simply dp of I comma t times I. So that's like simple. And yeah, so now we just need to like do this. So t. We have doubles. We have dp of doubles of size 2000 each. Then oh, p is constant? I did not realize that actually. Whoops. Okay, I was kind of solving a harder problem then. Yeah, I thought p was different for each person, because that was what that's what I thought the problem was, because that wouldn't be that much harder. If p is constant for if p is like different for each person, the solution will work. Well, does that make it easier then? I guess there's a different way to do this now. It's sort of like if we assume that people move on, then it's sort of like imagine we have like 5 seconds and we expect 3 people to come on. Then it's sort of like we pick the seconds in which 3 people will come on, and then yeah, we pick the positions in which 3 people will come on, and then we so this is 5 choose 3. And then so this has to happen 3 times, which is to say so it's p to the 3. And then it has to not happen on the other positions, which is to say we have times 1 minus p to the 5 minus 3, which is 2, of course. So I guess that would just like be it. All right. Well, yeah, that's another way to do it, I guess. So then this would actually be O of n. Is that what's intended? All right. Well, in a combinatoric sense, I guess this is a better solution. So, what do you want me to write? Do you want me to write the dp, or do you want me to write this one? Let's see, because it seems like a lot of other people wanted DP. So, who knows? Okay. Yeah, people want DP. Okay, so that's fine because like doing this is simple anyway, and I'm pretty sure I've included some other problem that will force me to compute binomial coefficients. So this isn't that big a deal. But this is a very simple formula to implement because this just is, yeah. All right. So let's see. So DP of 0 at 0 is 1. Otherwise everything else is 0. Not sure if memset works on doubles. I guess it's not a bad time to find out. So DP. Just didn't realize that was constant. 0, I is less than n, I plus plus. Yeah. For although j is equal to 0, j is less than or equal to t. I should do t first. Right? I am a mod. If you want to know that. Wait, what? Oh, okay. That is a good thing to note. Thank you. That switched. Okay, now, hello, prob is equal to p. If j is equal to n, prob is equal to 1. So actually, special case of if j is equal to n, then it's sort of just like this is the only option. So dp j I plus 1 plus equals dp ji. I'm sticking with dp of n and t here, so this many people, and then after this many seconds. So just sort of else here. dp of j, then what would it be? I plus 1 plus equals 1 minus p times dp ji, and dp j plus 1, having another person, plus equals p times dp ji. dp of I t times I. Can technically exclude the 0, it doesn't really matter. Point 0.5, 0.9375, 0.4. Yep, so very simple in terms of implementation. There's also the other formula, which is also quite elegant. Just this times this times this. This you can pre-compute in O of n, because it just works. This you can also pre-compute in O of n, and these. So in fact, this whole thing is just all pre-computation, and then you only have O of n things to sum up. So the whole problem can be solved in only O of n, and t just like, actually it's like, I guess this is, this would be, wait, actually no, this is O of t. And then this is, yeah. So it's like O of n plus t or something, I guess. Or maybe, I think it's bounded above by O of t. But anyway, it's just like math. Oh, did I indent the entire code? Nice. Oh, wait. Is given ith person enters only after 1 to n minus 1. Wait, what have I missed in chat? Can this be done with geometric progression? I don't think so. Or it might. I don't think so because there's sort of the choosing thing. Binomial distribution. Yeah, I remember that from stat. I just kind of forgot what it was. Let's see. Recursion? Yeah, I mean, doing recursion and sort of like this type of thing is very similar. Like, basically what you would have to do is just reverse this formula. So instead of adding these, you sort of like find some formula for dpij based on the previous values. I think this would be like, so for example, dp of, this is thinking of it recursively, dp of nt is equal to, special case of this being equal to 0, which I will ignore because I'm lazy, but say n is greater than 0 for like convenience, then it's p sub n minus 1 times dp of n minus 1 t minus 1 plus the other case that you come from something that hasn't changed, so it's 1 minus p sub n times dp of n t minus 1. So either you come from something that hasn't changed or you come from something that has changed. And then from here, this is a very simple recursive formula. You would implement the same thing, but stick in a function, and then it will work recursively. And of course, to convert this formula to iterative dp, you can just use the age-old trick of converting the parentheses to brackets. And then now you have it on an array, and then, it just goes on. Okay, let's see. So why is this correct? Because the ith person must enter after 1 to I minus 1. That's exactly what I'm using. Or wait, which one? The formula or the wait, which one are you asking about? The DP or this formula? Oh, the special case is just if we have n people, then we can't add another person because everyone's already gone. So the only possibility is that nothing happens. So it's just we have 100% chance of not getting another person, which is the same as this, except essentially p is 1. So in this special case, we can sort of set p to 1. It's not that big a deal. I mean, it's not that significant. Okay, you guys are asking about both of them? All right, so DP works because that's the whole point. The point is that one person moves after the other. So when you're at this person, it means that you already know that everyone else has gone before you, which means that you're only interested in what time this current person is going to move at. So that's like the whole point. If they can move in any order, this would be even harder, actually. Actually, I guess you would sort of do factorials, it would work out. Okay, and asking about the formula. So, the formula, this is a well-known thing called binomial coefficients. Basically, the order of the events happening doesn't matter. Because you know that no matter when these things happen, the first person's going to go first, the second person's going to go next, and so on. So we're really only interested in where these things are going to happen. And the where is, first of all, you need to know the positions. And the positions, you have 5 ways to choose the positions. And of course, this wouldn't matter what order actually, no. It sort of disregards order because the people move in a fixed order. So there's only one order for this to work. And then this just comes from the fact that in each of these positions, it has to be exactly, you have this chance of this being a 1, this being a 1, and this being a 1, and you have this chance of this not being a 1 and not being a 1. All these are multiplied because all of these have to happen simultaneously. Does that make sense? Which part would be the possibly wrong part? Wait, the how order doesn't matter. The first X people must enter, and the wait, there should not be 5 choose 3. Okay. I'm not choosing a subset of people. This is given that 3 people must enter the escalator in the first 5 seconds. So of the second, I'm choosing the seconds that people are entering the escalator on, not the people. So this is like, for example, time 1, time 2, time 3, time 4, and time 5. And I'm saying that someone must enter at time 1, someone must enter at time 3, and someone must enter at time 5. Which is necessary because it's like all of these are different possibilities, I suppose. All right, actually, is that true? That's a good question. I think maybe it has to do with counting. I actually forgot how this works. This is like a well-known thing that I remember learning from statistics, but like I think it is true, right? Like, so you have 0.5, for example, 0.5 to the 5, so that's over 32. What is 5 choose 3? Is that a big thing? Yeah, so it's like, pretty sure that is how it works. It's the probability of having... I'm trying to just like verify this for myself. By the way, if P isn't constant, the way to do this would be using dynamic programming. Because this only depends on the probability of each individual person. And in fact, I solved the problem assuming that P wasn't constant. So this DP formula would work. Although I don't think there would be a formula as nice as this one. Also, high demoralizer. Okay, right? So it's 5 choose 3, because that's the number of ways to have, like... Yeah, I know it's going to be correct. I'm just, like, trying to think of why now, because it's going to bother me if I don't. You have P cubed, because this is the number, this is the probability of that happening. And... I think it makes sense. Yeah. Otherwise, it would be kind of like weird. Okay. I think it's right. I'm not sure. Someone else can write that code if they want, I guess. Don't really want to write it though, because I've already done the other one. I'm just like kind of confused about probability, to be honest. This is not the best thing to have happen on a stream where I'm talking about probability. But you know, it's fine. I have water. You guys should get water if you don't have it. Yeah, because it's okay. Because it's the sum of the individual probabilities of each of those happening, and all of those contribute to the total because all of them have some possible chance, and they're mutually exclusive. So it's the sum of them. Okay. Right. Right. I remember this. Okay. I mean, I remember why that works now. So let's do this problem. We're 2 hours in. We're halfway through. I'm not sure how this is going to go. Yeah, sort of linearity of adding mutually exclusive things. I think that works. So I'm not going to read the text. With hands joined, go everywhere at a speed faster than our thoughts. This time the Fire Sisters is heading for somewhere they've never reached, water-surrounded islands. Okay. There are 3 clusters of islands, conveniently colored red, blue, and purple. The clusters consist of A, B, and C distinct islands, respectively. Bridges have been built between some, possibly all or none of the islands. A bridge bidirectionally connects 2 different islands and has length 1. For any 2 islands of the same color, either they shouldn't be reached from each other through bridges, or the shortest distance between them is at least 3, apparently in order to prevent oddities from spreading quickly inside a cluster. The Fire Sisters are ready for the unknown, but they'd also like to test your courage. And you're here to figure out the number of different ways to build all bridges under the constraints and give the answer modulo some number. 2 ways are considered different. Yeah. Okay. So, right. So we have a bunch of red islands. Let's put them in a line. Let's put these in a triangle, because that's sort of a nice way to think about it. They're not necessarily the same. We have some number of red, some number of blue, some number of purple islands. We want to add some edges between them. How much time does it take to make gym contests? It depends, like up to an hour, depending on how long it takes for problems. I should at some point ask other people to do it. I just haven't done that yet because yeah. So we have to add some edges, but the constraints are first, 2 things shouldn't be reachable. Or I mean, like any 2 nodes of the same color should either be disconnected or the shortest distance between 2 nodes of the same color is at least 3. Okay, so first of all, what that means is obviously they can't be directly connected, because if they are, then it's just not possible. Oh wait, I don't write problems. I sort of just find some. Like you see, all these problems sort of have different styles. I don't write them. Most of them are just past problems from the past. It would take way longer than an hour if I actually wrote these problems. Yeah, I'm not that cool to be able to produce a contest every week. Right, so we can't have any 2 things of the same color that are connected, because if we did, then they would immediately be 1 distance apart, and that wouldn't work. So the graph has to be quote-unquote tripartite, which is a thing. So then at this point, we have a tripartite graph. But there's also some other constraint we can have, because this only considers distance 1. What about distance 2? We also can't have nodes that are distance 2 apart. So say we have some cycle like this, some sort of triangle. And this is fine because it just kind of works out. But like say we have some edge here. Like say we just put down this edge because we have to add some edges somewhere. Then say we sort of add another edge to this node. It can't be to a red node. It can be to a blue node because that's fine. But say we add it to a purple node. Then this purple node and this purple node are distance 2 apart. First you go to this red node, and then you go from this red node to the other purple node. So you have a distance of 2, which is not possible because that's not allowed. So that's bad. And in general, this case will arise when you have any node of one color that's connected to 2 different nodes of the same color. Because if this is connected to 2 separate purple nodes, then you can go from this one purple node to this node and then to the other purple node, and the distance will be 2. So the constraint is not only can not only are we not allowed to have edges between nodes of the same color, but every node must also not have two edges to nodes of different colors. Which means that, for example, this red node can have at most one edge to a blue node, and at most one edge to a purple node. Now, is this enough? I don't think I will stream this weekend. I don't know. I'm doing the global round, sort of, unofficially, sort of, and then I want Saturday, kind of, so I probably won't stream on the weekend, I guess. I don't know. We'll see. So in terms of the problem, is this condition enough? The condition that, first of all, you can't have any edges between nodes of the same color, and you can't have some node that's attached to two different nodes of the same color. So, does a graph like this imply that all shortest paths are of length at least 3, or all shortest paths between the same color? Or do we need more constraints is the question. Well, let's say we have something like this. We have some red node connected to both a purple and a blue node. And then, for example, say we connect this in sort of a cycle. Then no matter what, like we don't have any blue nodes connected to any other blue nodes, so this is fine. So what we would instead want to do to try and break our case is to connect this purple node to another blue node. But then look, we go from a blue node to a red node, and then to a purple node, and then to a blue node. So it's distance 3, which is fine. And then even if we continue this chain, this can't be connected to a purple node because that would violate it, so we would connect it to a red node, for example. But then this red goes also a distance 3. Now if we continue this red can go to purple, for example, this purple can go to blue, and we continue. But no matter what we do, as long as we have the first two constraints, the paths will always be of length at least 3. That is the supposition. So why is that nice? Because, well, notice that these conditions kind of like don't depend on the other edges that we have. Like we can't have a red edge, we can't have a red node go to a red node, and we can't have it go to two purple nodes or two blue nodes. But there's nothing that says like any relation between, for example, this particular red node and a purple node and a blue node. Like sort of with this red node, whatever we do with purple doesn't depend on whatever we do with blue. And this holds for all nodes. So that's cool because now we're kind of solving 3 independent problems. We're solving the number of ways to attach red to purple, the number of ways to attach blue to purple, and the number of ways to attach red to blue. So, for example, like so. And then we're solving these 3 independent problems. And then we would sum them, or we would product them at the end, I suppose. Yeah. So now, simply, we just need to solve it for 1, and we have all 3. So we have a certain number of red nodes and a certain number of blue nodes. How would we find this? And the numbers are at most 5,000, which is probably important. So let's see. We were interested in the number of matchings in this bipartite graph, which is not a good way to represent it because that's like NP hard. So let's do something else. Consider this node. Like either we're gonna attach it to some blue node or we don't. But if we attach it to some blue node, then the number of ways to do so is equal to the number of blue nodes we have. And if we don't, then we have the same number of blue nodes, and now we're sort of like moving on to this one. So with this one, either we attach it to some blue node, and then the number of ways is the number of blue nodes we have, or maybe we attach some previous one, and therefore we have fewer blue nodes to work with, or we don't attach it at all. But the only thing we really care about when we get here is the number of blue nodes we have, because every arrangement of attaching things to blue nodes is going to be separate, which means we can count them all separately. There's no like sort of dependence. Which is cool because that means we're interested in two things, sort of. We're interested in the current node that we're at, the current node that we're drawing an edge from, and we're also interested in the amount of blue nodes we have left, the amount of blue nodes that don't have an edge to them. Now, why is that good? Because it means we only care about two numbers, the current node and the number of blue nodes. That sounds kind of nice. Indeed, why is that nice? Because now we can just do dynamic programming with this. We have the state reduced to two numbers. So we let dp of A and B, for example, be at the 8th red node with B blue nodes remaining. Yeah, now that's nice because wait, let's see, what's happened? Yeah, so this is sort of nice because the transition is simple. Either we attach a red node to a blue node and then we get, either we attach the current red node to another blue node, then we get dp of A plus 1, the next red node, and then B minus 1. Or don't, and then we get dp of A plus 1, and then B. So there are B ways to attach and one way to not attach. So this would be sort of B times dp of AB, and 1 times dp of AB. And in a sort of pushing sense, we would do it like that. Sort of thinking recursively, it's like we just sort of flip this formula. So this would be dp of A plus 1, B minus 1 is like B times dp of, so like for example, we can think of it the other way too. dp of A minus 1, B plus 1 times B plus 1. That's the transition of taking an edge. Or we can also think of it as not taking an edge, and then we come from dp of A minus 1 and the same number of blue nodes. Right, now this will just, it should just work, I believe. Yeah. So in a push dp sense, we are solving for this whole table. And then the answer for red and blue is the sum of dp of R and anything. Or the sum of dp of R and I equals, we can have 0 blue nodes up to B. And so to do that, we just like compute this. Let's see. I think we can do long longs. 5,000 times 5,000 times 8. Yeah, it's like barely enough space. But we do have space, I believe. So let's see, is there a way we can pre-compute this? Or should we just not every time? So this sort of depends on nothing, but what matters is this. I don't think it's possible to pre-compute because it sort of depends on what the initial state is. Yeah, I don't know. I don't think it matters that much. So, we're just sort of considering all three possible possibilities. Then we can define this function. Let me sort of compute dp like this. So dp of, so we initially start with a red node, or we initially start with on the 0th red node with b blue nodes left. So then for LL I equals 0, I is less than a, I plus plus. So we go down because we have to compute them in an order that we can push in. So let's see. So we can attach, in which case we have probability of B. Actually, we can not attach first. So dp I plus 1 j equals dp I plus 1 j plus simply dp ij mod mod. And the other case, if j is greater than 0, I plus 1 j minus 1. Then the number of ways to do it is we can take any of the remaining blue nodes. So we have j blue nodes, dp ij. Technically, we don't have to do the mod here every time, but it's not that big a deal. So dp of a and I. Mod. Right, this looks good, supposedly. We get 8. 63. What? 3264, and this big number. Okay, looks good. So by way of modular arithmetic, this is fine. We get very close to the memory limit, but it's also fine. I could theoretically make this int and then handle these transitions slightly more carefully, but it's not like that big a deal. Yeah, okay. So next part is to the next problem. I don't remember like which ones I chose to be probability and which ones aren't. Let's do this. Right. So current problem is G. Also, yeah, I don't see a reason right now to stop the topic streams, so can't hurt. Just, yeah. I mean, I don't see a reason to stop them, so I don't think I will. Okay, let's call a non-empty sequence of positive integers a1, a2, ak coprime if the GCD of all elements of the sequence is equal to 1. Given an array A consisting of n positive integers, find the number of its coprime subsequences. Since the answer may be very large, print it modulo 10 to the 9th plus 7. Note that two subsequences are considered different if chosen indices are different. For example, in the array 1 and 1, There are 3 different subsequences. So it's specifically not the values, it's the indices themselves. So their GCD must be 1. Alright. So to have the GCD be 1, there's like a lot of stuff that has to go on. Like, things are sort of, like all of the primes kind of have to like cancel out and stuff. It's like really not a good thing to want to deal with. So the point is, like, you could see this problem. You can think about trying to solve coprime things for a while, and you can eventually just like not get anywhere, and it's probably just not going to work out. So what would be nicer if we can perhaps count something else. What if we tried counting the complement? That is, counting the number of sequences such that their GCD isn't 1. And then there are 2 to the n minus 1 subsequences in total, so we can subtract that. So how many subsequences have GCD that isn't 1? Actually, I don't think that's even necessary. Well, okay. With the motivation of counting the number of subsequences that isn't 1, that aren't, such that their GCD isn't 1, let f of I be number of subsequences with GCD equal to I. How would we find f of 2? Well, clearly all of the numbers that could have a GCD, all the numbers that could be in a sequence of GCD2 have to have 2 as a divisor, otherwise it wouldn't make sense. So we could sort of isolate only the elements that have 2 in them. So let's say we have the sequence 1, 2, let's say we have the sequence 1, 2, 3, 4, 7, 8. Or no, 5, 6. I guess that's fine. Yeah, so we can isolate only the elements that have that are divisible by 2. So for example, we will have 2, 4, and 6. Now what? Well, okay. It may like be an initial idea maybe to just like count the number of subsequences that are in this array, which is 2 to the length minus 1. But that's not right, because like for example, 4 is a subsequence, and 4 is divisible by 2, sure, but its GCD is 4, which is a multiple of 2. Because the only constraint we have is that these numbers must be multiples of 2. I pinned the thing, right? Just to check. Yeah, okay. So given that we have to have a multiple of 2, what can we really do? Well, we can easily count the number of subsequences that are multiples of 2. Because, like, it's just the number of subsequences here. It's 2 to the, like, the number of them minus 1. So we can instead define this other function, g of I, to be the number of subsequences with GCD as a multiple of I. Which is simple, it's just 2 to the number of elements that are multiples of I. So that's fine, the only problem is that this doesn't actually give us an answer. Now there are 2 ways we can sort of turn this g function into the answer for the whole problem. The first way is to use principle of inclusion and exclusion. So for example, say we have 3 numbers, 2, 3, and 5. Then say we asked for all of the numbers that are like, let's say actually, would this be right? think it would be. I think what you'd want to do is you'd want to ask for the numbers that are multiples of all of these. And you would add these together. But then it sort of overcounts the number of ways to have, like, to be multiples of 2 of them, for example. So you have 2 times 3, you have 2 times 5, and you have 3 times 5. And all of these are sort of overcounted, because you would count them once for 2, and then you would count them once again for 3. And in fact, you don't want to count them at all. What you really want to, all you really want to get is the number of ways to have GCD be a multiple of I. Oh wait, I think there might be a better way. It's sort of like, it's sort of like you're interested in the number of ways to have no prime factors at all. Or rather, the number of ways for the GCD to be not 1, which means it has to have at least 1 prime factor. So we sort of add these, and then we subtract these, but then we're, like, once again, sort of undercounting the number of ways to have 3. So we add that back, and then we continue doing this for all the, like, all of the possible combinations of prime factors. Obviously, this is too slow, because, like we have, the numbers are up to 100,000. But instead, notice that we're only working with specific numbers that are up to 100,000. So instead of explicitly, like, counting these, instead of explicitly, like, going through like this, what we can instead do is we can simply go through each number, count its number of prime factors, and if this is odd, then you would, if you have, like, an odd number of prime factors, you would add them, so these two, and if you have an even number, you would subtract it. And it would sort of simulate this process of inclusion-exclusion using only the numbers that you really care about. So if you have a huge number that's a product of a ton of primes, maybe it's part of the formula, but we can, like, kind of ignore it because we know it's going to be 0, because it's bigger than 100,000. So no element will ever be a multiple of it. And then the answer is, like, the number of subsequences minus this, I suppose. So this is one way to do it. I'm pretty sure it's, like, come up a lot. And the only problem is that we have other things like this. For example, consider the number 2 squared times 3 to the 7th. Like, where do we put that? Because it technically has 9 prime factors, but the problem is they're, like, repeated. And the answer is, we can kind of ignore it. Like, we can just totally ignore things that are multiples of these types of numbers. And the reason this works is because when we're considering this, we're considering, like, only the unique prime factors. And so any number that falls under, like, this category of having a 2 and having a 3 will be treated the same way as 2 times 3 itself. So if we treat it the same way and we're doing this correctly, then we'll do the rest of these correctly too. So we sort of only consider numbers that have exactly one of each of its prime factors in the inclusion-exclusion. Because this will be counted as a multiple of this and, like, a multiple of these, and it will be correct. Okay, that sounds good. And in fact, there turns out to be this, like, very nice function that lets you sort of do this elegantly. Instead of, like, you can do this by like computing all the prime factors of a certain number and then using that to find the answer, like whether you should add or subtract or not do anything. But I think there's this thing called, like, the Mobius function or something. Is that what it is? Is it this or is it something else? Yeah, okay. It's the Mobius function. So it's just like mu of n. How's this? How do you draw this? So it's mu of n, which basically says 1 if. So, okay, if any of its divisors is a perfect square, for example, like this, one of its divisors is 3 squared. You also have 2 squared here. So if it has a square, then it's defined to be 0. If it doesn't have a square, but it has an odd number of prime factors, then it's -1. And if you have an even number of prime factors, then you have +1. So this is like a totally arbitrary thing, but it just so happens to exactly cover what we want from this. Because it's like, it just is exactly what we want. Like, we want squares to be 0 because we're kind of ignoring them. We want odd factors to be -1 because in terms of the total thing, we would actually end up subtracting this. So we can flip these signs. And then we want even factors to be +1. And so it's exactly the inclusion-exclusion we're trying to do. So we could sum up the values of Mobius of I times G of I. And that would work. Which is like kind of cool. But it's like not. It's just a fancy way to like represent this. And I think you can compute it with some sort of like linear sieve or something. Like the sieve of Eratosthenes, because you can figure out whether it has a square or not using that. So it's kind of cool in that sense. Although it's not really necessary, it's just a fancy way to represent this. But anyway, this is one way to do with inclusion and exclusion. Another way that I find like a lot easier is consider we want to find f of 2. So we can represent it as the number of ways to have a multiple of 2 minus the number of ways to have it be a multiple of 2 that isn't 2. How do I write this? So multiple of 2 that isn't 2. And then if we subtract, like, we have all the possible multiples, and then we have all the possible multiples except 2. So if we subtract this, we just get 2, like f of 2. So this, by definition, is g of 2, because it's just like what it is. And then this is equal to, well, it's equal to the number of ways to have every multiple of 2 except for 2 itself, which is to say f of 4 plus f of 6 plus f of 8, and so on, up until the maximum value. Now that's like nice because like if all that means is that like if we have these multiples, then we're just good, kind of. Now the problem is somehow we need to know the f values of the future ones. But for example, say like consider like g of 10 to the 5th, because 10 to the 5th is like the maximum. 10 to the 5th has no multiples except for 10 to the 5th itself. Which means that like g of 10 to the 5th is equal to f of 10 to the 5th. And in fact, this holds for any number where x is greater than 10 to the 5th over 2, because it means that none of its multiples will ever be included. Because they're just like too big. There are no multiples smaller than 100,000. So then, say we could try to compute g of 10 to the 5th over 2. We can see it as, actually no, we want to compute f of 10 to the 5th over 2. we can use the above formula. So it's g of 10 to the 5th over 2 there's no good way to draw this, is there? 10 to the 5th over 2 minus, again, f of the multiples, so minus f of 10 to the 5th. But that's like great, because we know that this is already correct. So then we can just figure this out because we know that its multiples are already correct, and we know g is just like a thing because we know it. So then if we go down, we know that all of the multiples of everything that's bigger than it is already going to be correct, provided that we go backwards. So the way to make this formula work is to iterate sort of backwards through the numbers. So we go from 10 to the 5th down to 1. So that's like great, except the only problem is that like this could take a while, right? Like we're summing potentially O of n terms n times. But like in reality we just aren't. Because the number of terms we sum up for I is n over I terms at most. Like it's the floor of n over I. And so with n over I terms, we're interested in the sum from I equals 1 to n of n over I, which is, like, by way of proof, this is O of n log n, which is, let's see. I think you can search this up. This is called the harmonic series. Yeah. So you can find this here. And basically, it's just like a proof that this sum comes out to O of n log n. So what that means is that the complexity of doing this is also going to be O of n log n, because it's like it just is it's just the number of terms we sum up. So really all we need to do is find g, go backwards, and subtract out all the multiples. No sort of like Mobius function mess or anything like that. We just straight up subtract out all the multiples. So for example, let's have two arrays. Then should we take only terms which are in the initial array? Yes. Because like they're the only ones that we can make subsequences from. In fact, what may be better is to have a count array, because then we can apply the same sort of harmonic series thing to F. Let's see, so max equals... Yeah, we can apply the same sort of harmonic series thing to F. Like, I mean, computing G, computing the number of multiples of I. So I mean, it's like, we store the counts of each array element, then, let's see, this is 10 to the 9th plus 7, which means you want to do it like so. Then we're like going here, so we 1, I is less than or equal to max, I plus plus. What do we do from here? We have to 0 for L of j equals I, j is less than or equal to max, j plus equals I. This is only counting multiples of I. Count plus equals Cj. By the harmonic series thing, this is O of n log n in total, so it's going to be fine in terms of complexity. Then gi is equal to Let's see. So it's 2 to the this thing minus 1. It's 2 to the count minus 1. So this is the point where I bring in binary exponentiation because it sort of like does things for us. So actually, I also wrote a blog on modular arithmetic, which kind of like does things. You can also there are videos as well for modular arithmetic, but I think this is good enough. I don't think I think it's necessary to explain on video. Actually, I'm just gonna like keep adding links. Because now I'm gonna copy binary exponentiation from my templates, which you can now find here. So this is very organized indeed. But I have this like number theory thing. No, it's not number theory. It's mod operations. And then from here, basically, this just lets you like compute exponentiation quickly. So we're looking for 2 to the count minus 1 because we can't take the empty subsequence. And then mod. The problem is this can be negative, so we can sort of like add mod to it, because now this makes it within the range of 0 mod. Or actually, it's within the range of negative mod plus 1, and so on. Meaning that if we add mod to this, it will be within the range of one, 2 times mod. And then if we mod that again, that means it'll be guaranteed to be positive. That's why I add mod there. Yeah, there are a lot of different modular things, I'm sure. Sort of like ways to explain binary exponentiation. But the point is it just computes like a power, like it computes 2 to the count modulo a thing quickly in O of log n. So that's nice. Right. Now I compute f, and this is simple. Max I is less than or equal to 1, I minus minus. For LOJ is equal to 2 times max, iterating over the multiples of max. No, 2 times I. Iterating over the multiples of I, then we subtract. So first set f of I is equal to g of I, then f of I is equal to f of I minus f of j, mod 1. We're just subtracting out all the multiples so that we're only left with f of I. Then f of I is equal to f of I plus mod. Because we're subtracting, we need to be careful about negative numbers. And the answer should just be f of 1. Because we're interested in the number of subsequences that have GCD 1. Right, I already have this. Five, 15, 100. Right. So again, keep the counts, do this sort of thing, do this harmonic series thing, then compute the G values, and then subtract, basically. And none of this should overflow, and none of this should be negative, I believe. Or wait, I think that should be... This technically shouldn't be a problem because the count is at most n, but actually, yeah, this won't be a problem because the count is at most n, so we don't need to care about overflow here. This still works, right? Yeah, we wouldn't care about overflow here because this will never be greater than mod. So I believe that's good. Indeed it is. So we are left with 3 problems now. Right, this one's fun. Okay. Petya was late for the lesson too. I assume this has to do with some problem on the contest. The teacher gave him an additional task. For some array A, oh wait. Yeah, there we go. For some array A, Petya should find the number of different ways to select a non-empty subset of elements from it in such a way that their product is equal to a square of some integer. 2 ways are considered different if sets of indices of elements chosen by these ways are different. Since the answer can be very large, you should find the answer modulo 10 to the 9 plus 7. So a square of some integer. Right. And this is combo because we're counting. This is like a DP stream in disguise. Alright, so we have numbers here. And if we kind of like break all these numbers down into their prime factor representation, as we normally would, for example, we have 1, 2, 4, 5, and 8, then this is equal to itself. This is equal to 2 to the 1. This is equal to 2 to the squared. This is equal to 5 to the 1. And this is equal to 2 cubed. Well, I mean, n is big. I mean, 2 to the n wouldn't work. What do you mean? What would you mean by O of 2 to the n? So we can sort of consider numbers like this. We can consider any subset we take as some number of 2's and some number of 5's. Where we need both x and y to be even for this to work because squares have even powers. Like just consider any number. 3 squared is 3 to the 2. 3 to the 4th is a square of 3 to the 2. We have to be able to divide all of the powers by 2 so that we can square them. So x and y must be even, which means we actually only care about their parity. So x can be either 0 or 1, y can also be either 0 or 1, and all of this is fine. Right, so now, in a sense, instead of prime factors, now we can represent this as kind of a binary number, where it's, like, we have a 0 in the 2 spot if we have an even number of 2's in our current product, and we have a 1 in the 2 spot if we have an odd number. And then the same for 5's. And then what we're interested in really is the number of ways to like pick a subset so that the total like value has a 0 in every bit. Now, what does it mean to combine elements? Well, it's sort of interesting that if we consider this like this is 0, 0, and then this becomes 1, 0 because we have an odd number of 2's here, then if we add the sort of things, each bit becomes like we add them and then take them mod 2, which is 0 plus 1 mod 2 is equal to 1, and then 0 plus 0 is 0. So to combine numbers, we take all of the bits and add them separately mod 2. But that's the same as what XOR is, which is very interesting. That because, like if we consider a truth table for x and y, then XOR is 0 when they're the same and 1 when they're different, which is the exact same result we get when we take the values mod 2. So it's not actually necessary to think of this as XOR, it's just like a representation of it. And I think at this point you could apply some linear algebra concepts and some like basis or something to be able to, or I don't know what it's called. But you can like find the number of subsets with 0 XOR. But anyway, that's kind of slightly irrelevant. So what we can instead do is we just need to find the number of subsets with XOR 0. And now the key here is that we return to the original problem. We don't get too lost in the reduction that we only have 70 values, which means that instead of representing it like as the values themselves, we can sort of create a count array of each of the values, then we only have 70 possible ones. So we create count I is equal to the number of instances of I. Okay. Right. So once we use this, then it's okay. I'm trying to think of this. Now the idea would be that we want like we would want sort of, I guess it would be more dynamic programming. Yeah, like I said, this is a DP stream in disguise. So we have DP of X, or no, like I and X, which is number of arrays with using the elements from only 1 to I, or maybe 1 to I minus 1, and then with XOR X. And the transition is, considering CI, either we take an even number of elements from this, or we take an odd number. And so the number of ways to take an even number is like, it's like CI choose J for even J, and then CI choose I for even I, or no, what? Choose J for odd J. It's just the number of ways to take even or odd. Because these elements do have a given order, which means that it doesn't matter the order we take them in, because we know their order will be predetermined by the elements we take. So it's just choosing. There's no like permutations or anything. So basically, we just need to like compute the counts, or we need to compute factorials. And choose k. So let's see. Let's have this value 75 and like some big thing, like 10 to the 5th. Put DP in the thumbnail. Yeah, views would stonk. Right. Okay. So I'm set C0 C. Wait, actually, how many primes will we have? This would be more than this. We'd have like a lot of possible values, I think. So what I can do now is I can copy my number theory template, and we can use this to find prime factors, which is nice. And again, if you haven't seen it before, my template is here in the description, so you can use that. Yeah. So we can start by, let's see, gen primes. Let's see, so it'd be just up to like 70, so we can do like 100 or something. Then prime list is automatically sorted. X equals count, plus count. X is greater than 70, break, because we're only interested in those primes. How many things do we have? Okay. So 19, which means we have 2 to the 19th, which means like 500,000. So we can do something like this. All right, then we also need n choose k. And to compute n choose k, we know that n choose k is equal to n factorial over k factorial times n minus k factorial, just a standard formula. And it's the number of ways to pick k items out of a set of n items. So we can compute factorials and inverse factorials. Factorial of at most 100,000. And this is my trick to do factorials. First, set the initial values to 1 and 0, or set the initial values of 0 and 1 to 1. Now, start from 2. Fact I is equal to I times fact I minus 1. This works because it's just like a basic formula, n factorial equals n times n minus 1 factorial. That's fine. Then now we use this other formula, that 1 over n factorial is equal to n plus 1 divided by n plus 1 factorial. Because if we like sort of cancel out the n plus 1s, we get n factorial. So therefore, if we compute the modular inverse of, which I need to do now, I guess. If we compute the modular inverse, which is also in my template, which is basically 1 over n factorial. The modular inverse of factorial of n, then we can go backwards, and we can use this formula, that I fact, the inverse of factorial I, which is just 1 over n factorial in the modulo realm. We have a modulo, right? Yeah, modulo 10 to the 9th plus 7. Otherwise, none of this would make sense. Yeah, okay. I fact I is equal to I plus 1 times I fact I plus 1 mod mod. Now we have factorials and inverse factorials. Now we can do n choose k. We can do the denominator. Which is simply k factorial, or 1 over k factorial times 1 over m minus k factorial. Turn, can't type. Right, because this is just n factorial times this inverse. Okay, so now that we did all the pre-computation, let's actually do the work now. So we have exactly one way to get dp of 0 elements with XOR 0. For Li equals what? 0. I is less than let's see, 70 I plus plus. I is less than or equal to 70, I guess. Yeah. Then now what we want to do is for each possible starting XOR, J is less than 2 to the 19th. Right, so first we have to compute the XOR value of like a certain number, and the way to do that is to find its prime factors. So this is another thing my template does. Helps to have a nice strong template that just does everything for you. So factors I, and in fact actually this time we would want to use 1 then. Right, so factors I, then and the answer would be 71, 0. Yeah. So for each factor, we add to the mask. If it has this factor, we add 2 to the position of that factor in our like sort of mask that we want, because that will simply set only that bit. Like if we add 2 to the 4th, 2 to the 2 to this, then we'll add 4, which will set this bit to 1, which is just what we want. We want to construct this mask. So it's the location of that value. So then the first possibility is take odd number of elements. Hello. First we should do this. So I'll do the count of odd things. J equals 1, J, let's see. J is less than or equal to Ci, J plus plus, J plus equals 2, iterating only over odd numbers, equals C odd times. So we have Ci choose J ways to pick this many numbers, given that this is an odd number. And then we do the same thing for even. Count even. Except this time we start at 0 because now we're only interested in even numbers. And then now we take odd. So dp I plus 1 j XOR the mask, because this is the old mask and now we get a new one, is equal to this plus C odd times dp ij. This is how much we push from this state to the other. We have this many ways of taking an odd number of things, which means that we the new XOR is XORed by mask. Otherwise, we take even. And then it's simple. The XOR stays the same. And that's it. Transitions are either we take odd or we take even, and then we're just kind of done, I think. I hope. I want to be, I want to be done. It's not very nice to debug though. Oh, because I haven't read in any input at all at this point. Okay, so this is the point where you would read in the array, I think. Yeah, for alright, so ++ count of AI, we memset count to 0 at the beginning. I don't need this value, right? Should only use the mask once. Yeah, I have not read in the input yet, which is interesting. Yeah, we get 0, which is wrong. So now we get to the fun part. Yeah, let's let this be 3. Then, I'm gonna have to remember to reset these values afterwards. DPI 0, right? So this should be the only thing that like matters. So this kind of dies. Why would that die? Maybe we need to count C odd. Do I have factorials wrong? I do have factorials wrong. Oh, yeah, yeah, you're right. That should be 1. Okay, that's stupid. I wasn't even setting them anything. Okay, we still get 0. Somehow that is a problem. Let's figure out 5, choose 3. Okay, so it's still wrong. I fact k times I fact m minus k. Right? I fact 3. Are these right? Or are these 0 somehow? Factorial of 5 is 0. Oh, that makes sense. N is 4. Okay, that's fine. Okay, that would be expected. But the rest of this doesn't make sense. So NCK41 is 4. But, like, what is this? Oh, wait, I see. Okay. We could also take nothing, and that's one way to have even. That makes sense. That still makes it wrong. So, dp of I and 0 shouldn't be 6. That does not make any sense whatsoever. Wait, this shouldn't have to be 1, because this is... If CI is 0, this whole thing should be 1. And so C even should be 1 anyway. So, what? So C odd is that. Why is C even not 1 by itself? What have I messed up? I choose K of 0 and 0 should be 1. It is 1. So it should be J equals 0, J is less than or equal to CI, J plus equals 2. So why is C even not always 1? What have I messed up? Oh, it's because it should be plus. God damn. Yeah, okay. This should be plus, not times. That's stupid. Now it's very, very close to right, but it's not. It should be 15. Are we overcounting 1 for everything? If so, then that's fine, because it means we're overcounting by 1 by the empty set, and that's okay. So this should be up to 70, this should be up to 19. If we're overcounting by 1 every time, then that's fine, because it means we're just including the case where we take no elements. So we get 8, and we should get 8 here. 4. Okay, that's a problem. So that is a problem, but this we would want to subtract 1. Yep. Mod. So the other one should work. But this one's like a problem. Why is this one a problem? This is 71 and 0. Okay, back to the drawing board. We only need 3 values here, so we can do 3. And then, wait. Right, the mask is messed up. Because what we really want is unique factors. Okay. Right. We only want unique factors, because otherwise, it wouldn't, like, it would be messed up. Actually, it's different. No, okay. Sorry. What I'm thinking is we want factors such that we have an odd number of them. If we have an even number of factors, then it's a square and we can ignore it. Okay, so now we kind of like do it like this. Pair LL X count. If x.second is odd, that is the number of them we have is odd, then now we add this. Okay, that is slightly very important. Now we should get 7, as expected, so the mask isn't messed up. Now we get 7. One more test. Let's do 7. We'll do squares. So 1, 4, 9, 16, 25, 36, 49. And the answer should be 2 to the 7th minus 1, which is 127. Yep, perfect. Okay, also check for overflow. Check for negative numbers. Good idea. Yep, so do this. Do the mod. Do it right. Do like up to 70. Make everything up to 70. Do the debugging thing. So do this mod. Do this mod. This is not going to overflow, so it's fine. This is mod. This is mod. This is all mod. And when we subtract, we add mod, so we can't have a negative answer. That looks good. Let's test where it's impossible. So we have 3, then we have, for example, 2, 3, and 5, and it should be 0. Let us see. I can read chat in the meantime. Yeah, 40,000 is pretty good. It's getting even better. How to be IGM in 1 week? I don't know. Maybe you should tell me that. In 1 week, you probably will be IGM. Yeah, I don't have school. I don't have classes on Wednesdays, so it works. People streaming on my server. That's kind of funny. And stamina. Okay, stamina is kind of just like do a lot of things. Like my first contest I did were Yusuko, which is like a 4 hour just marathon of stuff, and other things like just doing long contests and trying for a long time. And even if you get tired, just like keep going eventually, and it'll help you build your stamina. Because like the way to build stamina is just to like do things. And there's also like something else that you should like just be in a good mental state, like for example sleep, which is not something I've been good at lately, but it will help you because then you'll have just more energy in general. Okay, well, I guess we're gonna just wait for this to run for the rest of eternity. Just the rest of eternity. Yeah, sounds like it. Alright, one more refresh. Okay, in that case, I'm gonna grab lunch, I guess, because it's like 1 p.m. now. I'll be back in a slight. And then I think we can finish this in time, because the rest of the other two like aren't terrible. I think this was the hardest implementation of all of them. Q is just dead in general. Okay, I guess we'll yeah. Alright, I'm gonna grab lunch. I'll be right back. Actually, yeah, sure, that's a good idea. While we're here, what kind of future topics do you guys want to see? And then I will mark that as being at 3 hours and 18 minutes. So what kind of future topics do you want to see for things? Like, for example, now we're doing probability. You can take things from the poll. Yeah, it might just be DP. That's also a possibility. All right, yeah, I'll be back in a slight. Alright, back. Is this still running? Okay. What is the queue like right now? So, FFT number theory and graph theory. I guess I can't make a whole mashup on FFT. I don't even know it right now. I don't think that's gonna work. Just as an opinion. So status, how far does this go? Oh wow, yeah, okay, this just... Alright, so I'll save my program in a dump file for now, and then... Do I have anything here? No, I don't. This is good, right? Yeah, okay. So, save that here for now, and then we'll just move on to the next problem. Did I use the right mod? I did, okay. Alright, so we'll move on to I. That'll be how this works. Number theory tutorial? I'm not exactly sure. I mean, you could probably search one. I'm sure there's like a general thing on Codeforces, like Codeforces number theory. Yeah, and then you can find something like this. I don't know. Looks good. It looks like it covers things. Memory limit exceeded on test 1. Oh, what the hell? Am I using that much memory? Really? I don't. Wait, what? 75 times 500,000 times 8. Oh, it's just a bit too much. Okay. So I'll use int and then dp10. Yeah, that's fine. I don't think it'll overflow because it has long longs everywhere. This is long long, this is long long. Okay, that should be fine then. Should still compile it. Yeah. I didn't even consider memory. Are we waiting for the queue again? Yeah, we are. Okay. Please tell about where we should learn DSA and Algo. Just like in general, there's like a lot of things online for separate things. Like for example, I have some streams on DP, not to self-promote or anything, but you know, it is my own channel. And like there are just like resources everywhere. Like if you search up any sort of topic at all, you could find stuff on Codeforces, other blogs, videos probably. There are a lot of videos nowadays. Just a lot of possibilities. And Google is the best way to aggregate all of them to a single page. Why did I pick this one? This was not smart for me to do this. Why did I pick this problem? This is just annoying. Okay, in the probability theory, the following paradox called Benford's law is known. In many lists of random numbers taken from real sources, numbers starting with digit 1 occur much more often than numbers starting with any other digit. Which is interesting. And that's the simplest form of the law. And yeah, it's kind of a weird phenomenon. Having read about it on Codeforces, the hedgehog got intrigued by the statement and wishes to thoroughly explore it. He finds the following similar problem interesting in particular. There are n random variables, the ith of which can take any integer value from some segment Li on Ri. All numbers from the segment are equal probable. It means that the value of the ith quantity can be equal to any integer number from a given interval Li Ri with probability 1 over the possible numbers. The hedgehog wants to know the probability of the event that the first digits of at least k% of these values are equal to 1. Okay, you have a number n, which is the number of random variables. N is up to 1,000. Then I don't know why would they make it percentage? That doesn't even make any sense. Why don't they just make it a number? N is the number of random variables. Then follow n lines containing pairs of numbers li, each of whom is a description of a random variable. It's guaranteed that li and ri are between 10 to the 8th. 10 to the 18th. Yes, or at most 10 to the 18th. Okay, so we got H. Leaving us with 2 problems left. Fun. Okay. Right, so this one is just like do math, right? It's just like the same idea. Okay. So first of all, let's begin by finding the number of ways to have a 1 at all. So we have some interval L comma R. What's the probability of getting a 1 on this interval? Well, the probability is the number of numbers on this interval that have 1s minus the number of numbers in total. I mean, divided by the number of possible numbers. So the number of possible numbers is R minus L plus 1, as they give. How do we find the number of numbers that have 1 as their first digit? Again, as we did before, one convenient thing we can do is first we can count the number of numbers on the interval 1 to R, which means just the number of positive integers, and then subtract that from the count for 1 in L minus 1. This works because, again, we have this interval 1 to R, and we have this other interval 1 to M minus 1. How many times have I made this drawing now? Like hundreds? No, not hundreds, but a lot. L minus 1, and then we subtract out this one, leaving us with only the interval L to R. So that's what we can do. Now we need to count the number of values here that are less than that have 1 as their first digit. So first, say they have, so basically we're interested in f of x is equal to the number of 1s on 1 comma x. So first, we can consider the case of the number having less digits than x. Like, for example, say it has k digits, where k is less than the length of x. Then the first digit can be anything from 1 to 9. And then we have 10 to the k minus 1 possible other numbers. Which is like, that's just like the number of 1s we can have, because we fix a 1 here, and then we do like everything else. And then we can just have these be whatever digits they want, because they're numbers. And then we do this for all numbers. Yeah. So the only annoying case is kind of where we have k is equal to x, or k has the same amount of digits as x. And now we have to handle this case. Wait, h is less annoying finding a basis? Really? Nice. I guess if you can copy in the basis, maybe I guess it just works. I don't know. Same number of digits. Right. How's my day? Pretty good. No, I like streaming. And don't I have school right now? No, I don't have schools on. I don't have school on Wednesdays, which is why I insist on streaming on Wednesdays. Yeah, it's only Wednesdays that I don't have classes on, or and weekends. So this is like the best time to stream. You just got AC with basis, fever, and ores. Wait. I want to see this. So you just like copy paste the basis in and it works. Nice. What is this? Okay, I don't know how that works, but I trust it. Okay, well, anyway, so we have a thing going on. I can get rid of this now. Wait, I'm gonna get rid of this. Delete all of it. Okay, I've gotten slightly sidetracked, but this isn't like that bad. So if we have the same number of digits, let's just say the first digit is 1. And then, actually, now let f of x be some number of the form k, no, not k, just use k, like a and then the rest of the digits. So every other number b, which is less than a, it means you can have the full like number of numbers here. So it's 10 to the k minus 1. So that means is that if a is greater than 1, then you automatically get the full 10 to the k minus 1. Otherwise, if a is equal to 1, then you have 1, and then you have the rest of these digits. But this can be anything as long as it's like less than or equal to x itself. Which means that the number of ways you can do it is like x minus 10 to the like 10 to the k minus 1 or something. Or x minus 10 to the k, which basically means you just get rid of this ones digit, and then it's just the number of ways to have this number be equal to the rest of the digits of x. Sophie is rated 2623. I've confirmed this myself. It's like pretty scary. So basically that's what this casework is. Then once we have f of x, we have the probability of a number being 1 or not. It's just the number, like it's this divided by the number of numbers we have, r minus l plus 1. Have I tried leak codes contest? Not really. I think I did like 1 and then didn't do so well, but could try them again later maybe. So ow. Wait, is your rating really 6? Okay, never mind. That was exactly 623. That'd be funny. Right, now once we have the probability of something being 1, then we can just do this like very basically like the rest of the other ones. Let dp of n and c be the number of ways to have c ones from the first from the first n numbers. So basically the transition is very simple. Either you take a 1 or you don't. Then the probability of this is pi, and then it's 1 minus p, or pn and 1 minus pn. So you just like add pn times this to that, and then add 1 minus pn times this to that. And so this goes to dp of n plus 1, c plus 1, and this goes to dp of n plus 1, and just c because you don't have another one. And then the answer is just anything that's more than k%, or at least k%. So first we can find the values of p. So we can say p of n, no, not n, just like a number. C into n wait, so now C into k. Then LL ones equals f of LVI minus f of LVI. Then PI is equal to 1s over RVI minus LVI plus 1. Basic formula. So now we have to compute this F function. So current digit is equal to 1. So while current digit times 10 is less than or equal to less than n, then that means, like, for example, this digit is too small, so we can just add that. So of all numbers of this order of magnitude, we just have that many with 1 per digit. Just to test this, I'll print it. Then, let's see. So then x minus equals cur digit. If n is greater than or equal to cur digit, well, actually, basically this handles both cases at once. If a is greater than 1, then the answer, you add the current digits to that. And otherwise, you'll add n plus 1 because, like, for example, say the number is 105. Then you'll drop off the 1, then you'll have 05, and then any number from 0 to 5 will be valid. So it would be n plus 1 because it's, like, you also include 0. That looks good. I might have this whole indexing thing wrong, but I don't think so. Like, for example, say this is 105, then first current digit will be 1, and therefore there's one way to have that. Then it'll move to 10, and this is still valid because, yeah. And this is still valid because it's fine. Then you have 10 ways to do this. This number can be anything. and then this current digit will move to 100, and at this point it's too big, so now you handle that. Okay. Let's corroborate that with samples, although there are no samples. Why is that true? Oh, this should be LBI minus 1, of course. 0.5, and this should be 1/2 and 2/3. Yeah, okay, cool. So now we just simply do the other thing. How many ways to have n numbers having taken k ones? Or what's the probability, not how many ways. How many problems have I done this stream? Too many. Code Forces contests are 9:35 normally. Yeah, this is the 9th. I'm gonna finish this thing. I have one more after this. This one should be relatively simple after this. For I equals 0. If j is equal to n, then so it's the probability. So p I times dpij, dpi plus 1 j plus equals 1 minus pi times dpij. Right. And the answer is simply anything where we have more than k%. So we're interested in x is greater than or equal to k over 100, because k is an integer, times n, which is to say 100 times x is greater than or equal to k times n, meaning we don't have to deal with percentages. (100 times I is greater than or equal to k times n). Ants plus equals dp I n I. Cool. How was that? Oh, okay. Stretching. Good idea every once in a while. Wait. Oh, damn, really? I think overflow is genuinely going to be a problem here. Yeah, I think it would be. What? What is initializer? The only problem is that I need this to not overflow. I think I can get rid of this actually. So wait, LO max equals 2018 minus 1. And that way, when it gets to 1E18, it'll automatically break, which means that it won't reach this, I guess. The problem is that this shouldn't overflow. I don't want this to overflow, that's the problem. Okay, I think that works. That's a problem. Why is it not? Oh, because I didn't give it K. Okay, fine. 100. If I don't have this, except if I make this bigger, will it be wrong? I guess it's fine. I don't know. Can't hurt to be safe about overflow. Are we braving the queue again? Okay. Maybe that is overflow? I'm not sure. There could be problems here. Wait, this is right? 3, 4, 5, 6. Yeah. So let's see. What would be the problem here? Maybe we're doing the function wrong. So like, for example, we could stress this. 5, 1, 10, 125, 199. So this would be, oh wait. Let's see, 1 to 10, that's wrong. That should be, that is wrong. It should be 2. Why would that be wrong? Equals 0, return 0. Current digit times 10. Wait, what? So the problem would be, oh. I guess we would want this to be equal, and that's like the only special case that exists. I thought I was right about it. I thought it should have been less than, but I guess I'm wrong about that. 2. Okay, I guess that counts something extra. Wouldn't change anything else. Okay, yeah. Wait. So that works only because like a power of 10 is a special case. And so like that would be a bug that wouldn't come up in the samples, but it would be an issue because I want it to be, I want this to stop when it's on the same order of magnitude. But having this less than would mean that if n is a power of 10, now let's say this digit is 1000 and n equals 10,000, then this would stop even though it's not on the same because this is like a special case. And yeah, that fixes it. Okay. Cool. Probably should have tested that. Huh, that would have been smart. But whatever. Okay. So we have one left. Mike and geometry problem. Problem J, and alright. Mike wants to prepare for IMO, but he doesn't know geometry. So his teacher gave him an interesting geometry problem. Let's define f of LR equals r minus l plus 1 to be the number of integer points in the segment LR with L less than or equal to R. If it's a null set, then it's 0. You are given two integers n and k in n closed intervals li, ri on the OX axis, and you have to find this, this expression. The sum of over all possible subsets of the intersection of k segments. As the answer may be very large, output it modulo 10 to the 9th plus 7. Mike can't solve this problem, so he needs your help. You will help him, won't you? Did I pin it? I did pin it, right? Yeah, I did. Okay. Just to make sure, just to be safe. Made that mistake many times before. So yeah, Mike can't solve this problem, so he needs your help. You will help him, won't you? Chain n 200,000. Okay, so the fact that the bounds are so big means that any sort of DP or anything where we fix what the last segment is like just not gonna work. Somehow we have to be smarter than this. And one of the smart things we can do for combinatorics, which is to say we're counting the number of points that are covered by at least k segments. Actually, we're counting the number of, it's kind of weird, like for each subset we're counting the size of its intersection. But one smart way to flip the condition in terms of combinatorics problems is kind of very similar to the expected value thing, where we sort of compute it independently. What we're going to do is, this is a trick called contribution to the sum, where we basically ask, let's say we have some segments on space. For example, here we have 3 points on a number line, and we have one segment that covers this, one segment that covers this, and one segment that covers both of them. So let's find, instead of counting the sum of the intersections, let's find for each segment how many times it's included. How do we do this? Well, we're interested in the number of subsets of k segments that include this one. So first of all, we should find the number of segments that include this. And say we know the number of segments. Let that be k. No, not k. K we've already used. Why do I keep redefining the problem? K is a number. K is the number of things we need. So let this be c. We have c segments, and we need to find the number of subsets of size k that contain this. If you catch my drift here, this is just c choose k. It's the definition. Because it's the number of ways to pick k elements from c possible ones, as in subsets of size k from a total set of size c. So really, all we need to do is find this value c, and then sum up the values c choose k from all of them. How do we find the value c? Well, we could theoretically do prefix sums, but the problem is that the ranges are 10 to the 9th, so it's not good. What we could instead do is we can sort of say we have this big number line, and then we have a segment that goes here, and then we go here. And then we can say, for example, at this point, a segment begins, and then it will exist until its end, at which point the segment stops existing, and then a segment ends. So it's sort of like adding +1 to this segment, subtracting 1 at the end of this. Then if we were to go along and we were to sort of accumulate all of the numbers, all of the totals, here we would have 0, here we would have 1, and here again we would have 0. Which is perfect. So we do this for all the segments and it'll just work. We can do this with sort of a map, and then we sort of enumerate these coordinates instead of the instead of all of the 10 to the 9th things. We just sort of look at these individual coordinates. Right. So first we can compute factorials. So we can do n choose k. Okay. Actually, this input is the same, basically. That's kind of interesting. So, let's see. Fact 0, fact 1 equals I fact 0. Setting them equal to 1 this time. If you want to figure out what I'm doing here, you can check my thing for the 8th problem. I don't really see a need to re-explain it. I need mod op again, so I can get modular inverse. So fact n equals n fact n. Right. Now, hello, events. Also, okay. The right mod, right? 10 to the 9th plus 7. Yeah, okay. Just sending basic coding, basic factorial stuff. It may actually be smart to like put this in my number theory template or my mod op template. I think I'll do this later. Because, like, why not? Yeah, I'll probably just like put this in here and then add that to the GitHub or something. Okay, basically the idea here is I'm going to put all of the distinct points in a vector. And then when I find the sum on this range to this range, I can basically just like, it's like xi plus 1 or something. And this is xi, and then the range is just, the length of the range is just this minus this. Because it's, yeah. Vowels I plus 1 minus vowels I. Don't need to mod this because it's small enough. If cur so is the number of subsets nck cur k, then ants equals ants plus size times total mod mod. Oh boy. X dot first. One. What? Is this counting the complement or is it just totally wrong? Okay, it's just totally wrong. How would it be totally wrong? Oh, that? What exactly does it mean? And compile. I'll make it 3. Make it 2, okay. Something is slightly, very wrong here. You want to choose K. Should be RBI plus 1, maybe? I'm slightly confused. Okay, closed intervals is kind of hard to deal with. It's a bit annoying. I definitely don't understand that. Maybe this would not be... What? Doesn't make sense. It should get bigger. It should overcount. Wait, what? Oh, I didn't read in K. Seriously? Wait, how was I getting the right answer on 2 samples without even reading in part of the input? That actually makes no sense. 4. 0. What? What? Okay, none of this makes any sense. Does not make any sense at all. Okay, wait. Just print everything. So it should be 5, but it's not. So, wait, actually, this one should not be wrong. This is like the simplest sample. So 3 and 0. How would this be 0? Is this wrong again somehow? Fact 0, fact 1, I fact 0, I fact 1. So it's I times fact I minus 1. I'm in fact n. I don't understand. At some point I should write and choose K and then just like not screw it up ever again. That would be great. Oh, toad is 0. I mean cur is 0. Because it should be vowels I. Yep. Seems legit. 3. Didn't run the program. 5. 6. Okay. Didn't run the program. Yeah, that's stupid. Okay, wait. Let's make sure. Read into n to k. So read in the intervals. Set the factorials. Do the thing. make the events happen. This is an inclusive interval, so put RV on the outside. Then, because like on this interval L to R, like for example on this interval L to R, everything should be 1. And then only at R plus 1 should it be different from 1. I mean, should it be not 1 anymore? So then take the size, count the the events, do n choose k, and then count the answer. Seems legit. Only problem could be overflow, I guess. Or I could die on test 1. Oh, okay. Test 34. Alright. That completes this mashup. Like barely over 4 hours. That's actually pretty good. I picked a lot this time because I don't know. I made this one easier. Like this one was only 2000. The highest difficulty was 2000, unlike last time. So it was slightly easier at the cost of having more problems. Which is fine, because there are a lot of possible topics for combo. And like probably like there are many that I didn't even cover here. So we might be able to have another stream of this. I don't know. In any case, I'll have to learn combo myself, which is very, very certainly a good idea. So, yeah, alright, for this, it is over now. Let me read chat and then we'll finish the stream because I have nothing else to do. Yeah, 4 hours, that's like normal. That's like the normal time now. How am I able to focus for so long? Well, again, like things like Yusuko are 4 hours long, things like IOI are 5, so it's just sort of a requirement to be able to do that. And so to practice, you can just do either long practice sessions, like this, for example, or like virtual, these sorts of IOI and Yusuko contests, the sort of things that last a long time. And then you'll build up endurance by just doing things a lot. Prerequisite? Not sure. I mean, most of it should be self-sufficient, I suppose. Maybe trees are a bit more advanced. Like, at least the beginning stuff is mostly basic things. Like, for example, this is just, like, figure out a formula and or do a geometric progression. So, yeah, it's not like that advanced. You can probably get into it with very little background knowledge. So, regular practice, or was I focused from the beginning? Well, I do like doing this, for one. It's kind of satisfying to, like, be able to do things. And also, I had the motivation of wanting to beat my friends, so that was kind of a thing. Yeah, that made it more fun to sort of, like, have that competition in mind. And so from that, I was able to practice a lot, because I had motivation to, and that's kind of the most important thing. If you like it, then you'll be able to do it more. And if you, like, have a reason to. So I just had a lot of motivation, and that turned into focus, I suppose. But yeah, in terms of endurance itself, just do a lot of long things. Like, you can just straight up grind for 4 hours in a row like this, and then... I mean, if you have that time, you could try long things, I suppose. Do I do type racer? We can try that afterwards. If you want to talk to me more, you can join this Discord that's in my description, and I'll be there. It's perfect. It's a great way to talk to someone. Just saying. What are prerequisites? I would say not much. I think not many prerequisites. Mostly things should be self-sufficient. Like the stream should be good enough on their own. Maybe not trees. If you don't understand what a graph is, I guess you would want to learn that. And probability, like you should have a fundamental basis of school math, I believe. And then DP is its own thing. So it's probably fine. DP is fine on its own without prerequisites. Yeah, 10 greens are pretty satisfying. Although my status isn't so satisfying because I had these things, which is a bit sad. But, you know, it was close. If we scroll down a little bit, looks pretty good. Yeah, I'll see what I can do about a microphone. Eventually it'll be better. Right now I'm just using my laptop mic, because I don't have a budget. Is use code training still relevant? Yes, definitely. I think it's good, and it got me to become pretty, like, good at it. So I think it's good. Next poll have FFT. I don't even know FFT myself. How am I going to do that? Alright, yeah, okay, I have nothing more to do. I'll end the stream here. If you want to ask more questions, join the Discord. It'll be good. Geometry possibility. Ba-boom. Wait, okay. The special case in E? The special case was just you already have n people, so you can't have another person. So the only thing you can do is go further in time without having anyone get on the escalator. So you have a 100% chance of nobody getting on the escalator and a 0% chance of somebody. Alright, everything will be on a poll. Geometry will be on a poll. If you want it, vote for it. Alright, I'll be off. See you guys.